The stars shine, but not forever. Galaxies glow, but only for a while. One day all light will fade. One day the universe will be quiet. This is not a story of fear, but of wonder, of how everything we know comes to an end. In the vastness of space, we are but a fleeting moment, a brief flicker in the cosmic timeline. Yet in that flicker, we have come to understand so much about our universe, its past, and perhaps most hauntingly, its future. Tonight, we journey together through time, far beyond the span of human civilization, beyond the life of our sun, beyond even the existence of stars themselves. We will travel to the edge of time, where the very concept of existence becomes something altogether different. The universe we know today is vibrant and alive. Galaxies spiral through the darkness, stars ignite in brilliant fusion, planets orbit in quiet persistence. But nothing lasts forever, not even the cosmos itself. Close your eyes and imagine the night sky, those countless stars, each a sun to potential worlds we may never know. Now imagine that sky growing darker, star by star, until only blackness remains. This is not simply possible, but inevitable. The story of our universe's end is written in the physics that governs everything around us, the same forces that brought atoms together, that ignited the first stars, that formed the galaxies, will eventually unravel it all, not in violence, but in whispers, not in chaos, but in the quiet fading of light. As you drift with me through these cosmic timescales, remember that we are privileged to exist in the universe's bright youth. We live in an era of creation, not dissolution. The stars still burn, the galaxies still dance. Life still emerges in the sheltered corners of at least one world. The end may be certain, but it is unimaginably distant. What awaits us tonight is not a nightmare, but a meditation on time and existence. A gentle contemplation of the greatest story ever told, from its vibrant middle to its quiet conclusion. Let the darkness around you become the canvas of deep space. Let your breathing match the slow pulse of cosmic time. Feel yourself becoming untethered from the brief moment we call the present. The journey we are about to take spans trillions upon trillions of years. We will witness the last stars fade, the last planets cool, the last black holes evaporate. We will see the fundamental forces that shape our reality play out their final acts. And perhaps, in understanding the end, we might better appreciate the remarkable now in which we exist. So lie back, breathe deeply, and let us begin our journey through the greatest time span imaginable, from the universe we know to the universe that will be, from light to darkness, from complexity to simplicity, from everything to the whisper of what once was. This is the end of everything, and it is beautiful. To understand how things end, we must first understand what is and what forces shape our destiny. Our universe began approximately 13.8 billion years ago, not with a flash but with an expansion. Space itself stretched outward from a single point, carrying with it the seeds of everything we know. In those first moments, energy congealed into matter, particles formed, atoms assembled, and the fundamental forces that still govern our reality took shape. Today, we find ourselves in a universe of remarkable complexity and beauty. Our home is the Milky Way galaxy, a vast spiral of stars numbering in the hundreds of billions. Our sun is but one of these stars, burning steadily in its middle age, providing warmth and energy to our small blue planet. But our galaxy is just one among trillions. When we look up at the night sky with our most powerful telescopes, we see a cosmos teeming with galaxies of all shapes and sizes, spirals like our own, ellipticals, vast and featureless, irregulars, chaotic and cloudy. Each contains billions upon billions of stars. Each star potentially cradles worlds, and some of those worlds might harbor life. Between these galaxies stretches the cosmic web, filaments of dark matter that guide the movement of everything visible. This invisible scaffolding makes up about 27% of our universe. Ordinary matter, the stuff we can see and touch, accounts for a mere 5%. The remaining 68% is something even more mysterious, a force we call dark energy. The universe we observe today is approximately 93 billion light-years across. But this is only the observable universe, the part whose light has had time to reach us since the beginning. The true extent of space likely stretches far beyond what we can see, perhaps infinitely, and it is growing. Our universe expands with every passing moment. Galaxies drift away from one another, carried by the stretching of space itself. This expansion is not just continuing, but accelerating, driven by dark energy, a mysterious pressure that pushes outward against gravity. We can glimpse the universe's history by looking at the cosmic microwave background, a faint glow that permeates all of space. This is the afterglow of the Big Bang, the oldest light in our universe. It shows us that the cosmos was once much hotter and denser than it is now. As we observe distant galaxies, we see them as they were in the past, their light having traveled to us across billions of years. The farthest galaxies we can see appear as they were just a few 100 million years after the universe began. They are smaller, more chaotic, and forming stars at a furious pace. Closer to us in both space and time, galaxies appear more mature. Star formation has slowed, structure has settled. The wild youth of the cosmos has given way to a more ordered middle age. Here on Earth, we experience this universe through the 5 fundamental forces. Gravity binds us to our planet and keeps Earth in orbit around the Sun. Electromagnetism allows us to see light, feel warmth, and experience the chemical reactions that make life possible. The strong nuclear force holds the cores of atoms together. The weak nuclear force enables certain forms of radioactive decay. And perhaps a 5th force, dark energy, drives the accelerating expansion of space. Our understanding of these forces comes through careful observation, mathematical modeling, and technological innovation. With particle accelerators, we probe the smallest scales of reality. With space telescopes, we peer into the depths of time and space. With theoretical physics, we attempt to unite our observations into a coherent picture of how the universe works. We know that stars form from clouds of gas and dust, igniting when gravity compresses their centers enough to trigger nuclear fusion. We know that stars die in various ways depending on their mass. Some explode as supernovas, scattering the elements they forged into space. Others fade slowly into white dwarfs. The heaviest collapse into black holes, regions where gravity is so intense that not even light can escape. These processes have been occurring for billions of years and will continue for billions more, but not forever. The universe is changing, its resources are finite, its energy is dispersing, its bright youth is giving way to a different kind of future. The stars we see in the night sky tell us about the present state of our cosmic neighborhood, but they also hint at what is to come. In their life cycles, we see echoes of the greater life cycle of the universe itself: birth, maturity, decline, transformation. We stand at a privileged moment. The universe is old enough to have developed complexity, galaxies, stars, planets, and life. Yet it is young enough that it still brims with energy and potential. We live in the era of stars, when light still crosses the vast gulfs between galaxies, when matter still coheres into complex forms. But this will not always be so. As we look ahead through cosmic time, we see changes coming. Slow at first, then increasingly profound. To understand how things end, we must first understand what is and what forces shape our destiny. Everything in our universe, from the smallest subatomic particles to the largest galactic superclusters, is governed by 4 fundamental forces. These forces, working in concert or in opposition, shape the destiny of all matter and energy. They built the cosmos we see today, and they will orchestrate its eventual end. Gravity is perhaps the most familiar of these forces. It draws matter toward matter, creating an invisible bond between all things that have mass. Gravity is what keeps us anchored to Earth, what keeps Earth orbiting the Sun, what binds stars together in galaxies. Though it seems powerful in our daily experience, gravity is actually the weakest of the 4 fundamental forces. Its strength lies in its range, reaching across the entire universe, never diminishing to zero. Gravity works by warping the fabric of space-time. Massive objects create depressions in this fabric, like heavy balls placed on a stretched rubber sheet. Other objects follow the curves created by this warping. The more massive an object, the deeper the depression it creates, and the stronger its gravitational pull. This is why a black hole, with its immense mass concentrated in a tiny space, creates such a powerful gravitational field that not even light can escape. The second fundamental force is electromagnetism. This force governs the interaction between electrically charged particles, binding electrons to atomic nuclei and atoms to one another. It is responsible for chemical reactions, for the light that illuminates our world, for the electrical impulses that power your thoughts as you listen to these words. Electromagnetism is much stronger than gravity at close range. It is what prevents you from falling through the floor, as the electromagnetic repulsion between the atoms in your feet and the atoms in the floor creates the sensation of solidity. Yet unlike gravity, electromagnetism can both attract and repel. Opposite charges pull toward each other, while like charges push apart. The third fundamental force is the strong nuclear force. As its name suggests, this is the strongest of the four forces, but it operates only at incredibly small distances within the nucleus of an atom. The strong force binds protons and neutrons together, overcoming the electromagnetic repulsion that would otherwise push protons apart. Without the strong nuclear force, atoms larger than hydrogen could not exist. There would be no carbon for organic molecules, no oxygen for breathing, no iron for planetary cores. The strong force enables the nuclear fusion that powers stars, converting hydrogen into helium, and in larger stars, creating all the heavier elements up to iron. In the heart of every star, the strong force works against gravity, preventing stellar collapse while fusion can continue. The fourth fundamental force is the weak nuclear force. Like the strong force, it operates only at subatomic distances. The weak force is responsible for certain types of radioactive decay, processes in which one type of subatomic particle transforms into another. It helps facilitate nuclear fusion in stars and played a crucial role in the production of elements in the early universe. These four forces emerged during the first moments after the Big Bang, separating from what may have been a single unified force as the universe cooled. Their relative strengths and properties determined how matter would behave, how elements would form, how stars would burn, and how galaxies would evolve. But there is possibly a fifth force at work in our universe, one whose nature remains deeply mysterious. Dark energy appears to act as a kind of anti-gravity, pushing space itself to expand at an accelerating rate. Unlike the other forces, which generally grow weaker with distance, dark energy seems to maintain a constant strength across space. This means that as the universe expands, the influence of dark energy grows stronger relative to gravity. In the cosmic ballet, these forces dance together. Gravity pulls matter inward, forming stars and galaxies. The strong and weak nuclear forces enable stars to shine, converting matter to energy. Electromagnetism binds atoms into molecules, enabling the complexity we see around us. And dark energy pushes everything apart, stretching the cosmos ever larger. But this balance will not last forever. As the universe ages, the dance of forces will change. Gravity will continue to pull matter together, but as galaxies drift apart due to cosmic expansion, its influence across the largest scales will diminish. Stars will exhaust their fuel, and the nuclear forces will have less material to work with. Electromagnetism will continue to bind atoms, but in a cooling universe, complex structures will become less common, and dark energy will continue its relentless expansion, eventually dominating the cosmic stage. The interplay between these forces, particularly between gravity and dark energy, will largely determine the ultimate fate of our universe. If dark energy remains constant, the expansion of space will continue to accelerate. Galaxies will drift beyond each other's visible horizons. Gravity will be unable to pull new material together to form new stars. The universe will grow colder and darker. In the most immediate future, gravity still shapes the local universe. Our Milky Way is on a collision course with the nearby Andromeda Galaxy, drawn together by their mutual gravitational attraction. In about 4 billion years, these two spiral galaxies will merge into one larger elliptical galaxy. Other small galaxies in our local group will eventually join this merger, pulled in by gravity despite the universe's overall expansion. But beyond our local group, gravity is losing its battle with dark energy. Distant galaxy clusters are already moving away from us faster than the speed of light, carried by the expansion of space itself. In the far future, any observers in our galaxy would see an increasingly empty sky as other galaxies recede beyond the observable horizon. This is the grand cosmic tension that will shape the end of all things. The tug of war between the inward pull of gravity and the outward push of dark energy. And on this vast stage, with these fundamental actors, the final acts of our universe will play out across timeframes that defy human comprehension. These forces built the cosmos, but they will also determine its end. The stars that illuminate our night sky represent the universe in its prime, an era of light and creation that has persisted for billions of years. But this stellar age will not continue forever. Even now, the universe is changing, gradually transitioning from a time of abundant star formation to one of increasing darkness. Stars are born from vast clouds of hydrogen and helium gas, the primordial elements that have existed since shortly after the Big Bang. When these clouds become dense enough, gravity pulls the gas inward until temperatures and pressures reach the threshold for nuclear fusion. The cloud collapses, a protostar forms, and eventually, a new star ignites, pushing outward with radiation pressure to balance the inward pull of gravity. This process has been occurring throughout the cosmos for more than 13 billion years. The first stars formed when the universe was just a few 100 million years old. They were giants, hundreds of times more massive than our Sun, burning hot and bright and dying quickly in spectacular explosions. These first stars forged heavier elements in their cores and scattered them across space when they died, enriching the cosmos with the chemical building blocks for planets and, eventually, life. Subsequent generations of stars formed from clouds already seeded with these heavier elements. Our own Sun is one such star, a third-generation stellar citizen born about 4.5 billion years ago. It is a middle-aged star now, with another 5 billion years of stable burning ahead of it. But across the universe, star formation is already slowing down. We have passed the peak of stellar creation. Studies of distant galaxies reveal that star birth reached its highest point about 10 billion years ago, when the universe was just 3 to 4 billion years old. Since then, the rate of new star formation has been declining. This slowdown occurs because the raw materials for stars are gradually being depleted. The vast molecular clouds that serve as stellar nurseries are finite resources. Each generation of stars consumes some of the available hydrogen and helium, converting it to heavier elements through nuclear fusion, or locking it away in stellar remnants like white dwarfs, neutron stars, and black holes. At the same time, galaxies are running out of gas. Fresh hydrogen was once abundant throughout the universe, drifting between galaxies in great clouds that could fall into galactic disks and fuel new generations of stars. But this process is becoming less efficient. Dark energy pushes galaxies farther apart, making it harder for them to capture new gas from their surroundings. Many galaxies have already consumed most of their original gas supplies, while others have had their gas stripped away through collisions or interactions with neighboring galaxies. We can observe this stellar decline by looking at different types of galaxies. Spiral galaxies like our Milky Way still have significant gas reserves and continue to form new stars, particularly in their spiral arms. But elliptical galaxies, which make up about 60% of all galaxies in the modern universe, have largely exhausted their gas supplies. They contain mostly older stars and form few, if any, new ones. The process of star formation itself is an intricate dance of opposing forces. Gravity pulls gas clouds inward, while heat, magnetism, and the pressure of radiation push outward. For a new star to form, gravity must win this initial battle, compressing the cloud until its core becomes dense enough and hot enough for fusion to begin. In the early universe, this process was highly efficient. Vast, pristine clouds of hydrogen and helium collapsed under their own weight, forming the first generation of stars. These stars were unlike any that exist today, composed almost entirely of the lightest elements, with virtually no metals. Astronomers call these theoretical population 3 stars, and while we have never directly observed one, their brief existence is written into the chemical composition of the oldest stars we can see. These first stars burned hot and bright, some reaching hundreds of times the mass of our Sun. Their immense gravity compressed their cores to enormous temperatures, accelerating their nuclear fusion reactions. As a result, they exhausted their fuel in just a few million years, a mere eye blink in cosmic time. Their deaths as supernovae scattered the first heavy elements throughout the cosmos, setting the stage for more complex chemistry. The second generation of stars, called Population 2, formed from clouds lightly enriched with these heavier elements. They can still be found today in the halos of galaxies and in globular clusters. ancient stellar cities that orbit the Milky Way like moths around a flame. These stars contain modest amounts of elements heavier than helium, perhaps 0.1% of their total mass. Our Sun belongs to a third generation, population 1, formed from clouds significantly enriched by previous stellar generations. About 2% of our Sun's mass consists of elements heavier than helium, the accumulated product of billions of years of stellar nucleosynthesis. These metals, as astronomers call all elements heavier than helium, enable the formation of rocky planets like Earth and the complex chemistry that makes life possible. But this progression cannot continue indefinitely. The universe has a finite supply of hydrogen and helium, the primary fuels for stellar fusion. With each generation of stars, some of this fuel is locked away in stellar remnants or converted to heavier elements that are less useful for powering new stars. Already, the cosmic star formation rate has declined to about 1/10 of its peak value. In the local universe, only about one solar mass worth of new stars forms each year in a typical galaxy, compared to 10 or more solar masses per year during the universe's most active period. This decline will continue, accelerating as galaxies exhaust their gas supplies, and as cosmic expansion makes it increasingly difficult for galaxies to accrete fresh material from their surroundings. The last major wave of star formation in most galaxies will likely occur following significant mergers, when the gravitational disruption drives remaining gas to collapse into new stars. For our own Milky Way, this final burst of stellar creation may come about 4 billion years from now, when our galaxy collides with Andromeda. The merger will trigger the collapse of any remaining gas clouds, leading to a brief but spectacular period of starbirth. But once this gas is consumed, little material will remain for future generations of stars. Beyond our local group of galaxies, the picture is even more stark. Cosmic expansion is accelerating due to dark energy, causing distant galaxy clusters to recede from each other at ever-increasing speeds. Eventually, these clusters will be so far apart that they cannot interact or exchange material. Each cluster will become an island universe, isolated and limited to its existing resources. Over the next few trillion years, more and more galaxies will transition from active star-forming spirals to quiescent ellipticals. The bright blue stars that currently dominate the light output of the cosmos will die off, leaving behind the smaller, redder, longer-lived stars. These red dwarf stars, with masses between roughly 10 and 50% of our Sun, burn their fuel much more slowly and efficiently. A typical red dwarf consumes its hydrogen at such a leisurely pace that it can shine for trillions of years. The smallest of them might burn for up to 10 trillion years, nearly 1,000 times longer than the current age of the universe. These modest stars will be the final torchbearers of the stellar age, the last conventional fusion-powered objects in a darkening cosmos. The reason for their extraordinary longevity lies in their internal structure. Unlike our Sun, which has a radiative zone where energy moves outward through radiation, red dwarfs are fully convective. This means that currents of plasma circulate throughout the star, mixing hydrogen fuel from the outer layers into the core where fusion occurs. This allows the star to use nearly all of its hydrogen for fusion, rather than just the approximately 10% that stars like our Sun can access. Furthermore, the nuclear reactions in red dwarfs proceed more slowly due to lower core temperatures and pressures. Where our Sun fuses hydrogen at millions of degrees, a red dwarf might operate at just a few million degrees. This reduced rate of fusion extends the star's lifespan dramatically. As we move tens of billions of years into the future, the night sky, as seen from any surviving planet, would gradually change. The bright blue and white stars would disappear first, burning out within a few billion years of their formation. Yellow stars like our Sun would follow, exhausting their fuel and swelling into red giants before shedding their outer layers as planetary nebulae and contracting into white dwarfs. By 100 billion years from now, all that would remain are the red dwarf stars and the stellar remnants, the white dwarfs, neutron stars, and black holes left behind by previous generations. No new stars would form in most galaxies, as the remaining gas would be insufficient to collapse into new stellar nurseries. The universe would grow dimmer and redder. Where once the cosmos blazed with the blue-white light of massive hot stars, it would now glow with the subdued crimson of countless red dwarfs. The spectacular nebulae, those vast clouds of glowing gas energized by the radiation from hot young stars, would fade away. The explosive supernovae that periodically brighten galaxies would become increasingly rare events. And still, time would pass. 1 trillion years. 10 trillion years. The smallest red dwarfs would soldier on, fusing hydrogen into helium in their cores at the barest minimum rate needed to maintain stellar equilibrium. Their feeble light would illuminate a universe increasingly dominated by darkness. But even these enduring stellar embers must eventually go out. A red dwarf, despite its longevity, still has a finite supply of hydrogen fuel. As this fuel is exhausted, the star would gradually heat up and swell slightly, fusing the last of its available hydrogen. With no mechanism to create the internal pressures needed for helium fusion, the star would simply cool once its hydrogen was gone. Unlike more massive stars that die in dramatic fashion, red dwarfs would face a quiet end. They would grow brighter for a brief period near the end of their lives, then slowly fade as their fusion reactions sputtered out. With insufficient mass to collapse their cores to the temperatures needed for further fusion, they would simply cool and dim, transitioning smoothly from red dwarfs to white dwarfs without the intervening giant phase that more massive stars experience. The last of these red dwarfs would fade out approximately 10 to 20 trillion years from now. This would mark the end of the stellar era, a span of time nearly 1,000 times longer than the universe has currently existed. After this, no conventional fusion-burning stars would illuminate the cosmos. The only sources of light would be the cooling embers of dead stars, the white dwarfs and neutron stars gradually radiating away their residual heat, and the occasional flare from material falling into a black hole. The age of stellar light, which has defined the universe since its earliest epochs, would finally come to a close. The sky may remain lit for eons, but one by one, the lights will blink out. When the last red dwarf star flickers out, roughly 10 to 20 trillion years from now, the universe will enter a new phase of its existence. Astronomers call this the degenerate era, a time dominated not by the bright fusion fires of conventional stars, but by the cooling remnants they leave behind. White dwarfs, neutron stars, and black holes will become the primary occupants of the cosmos, drifting through an increasingly empty and dark universe. White dwarfs will be the most numerous of these stellar remnants. These are the cores of stars like our Sun, left behind after they exhaust their nuclear fuel and shed their outer layers. A typical white dwarf contains approximately 60% of its parent star's mass, compressed into a sphere roughly the size of Earth. This makes them incredibly dense, with a teaspoon of white dwarf material weighing several tons. Despite their name, newly formed white dwarfs shine with a white or bluish light, their surfaces scorching hot at temperatures exceeding 100,000 degrees Celsius. But with their nuclear fires extinguished, white dwarfs have no internal energy source. They simply radiate away their residual heat, gradually cooling over immense spans of time. A white dwarf's cooling process begins rapidly, but slows dramatically as its temperature decreases. After 1 billion years, a typical white dwarf might cool to about 10,000 degrees Celsius, glowing with a yellowish light. After another billion years, it might reach 5,000 degrees, appearing orange. After 10 billion years, perhaps 3,000 degrees, a dull red. But the cooling continues far beyond this point, albeit more slowly with each passing eon. After 1 trillion years, the surface temperature might fall to a few hundred degrees Celsius, too cool to emit visible light but still radiating in the infrared spectrum. And still, the cooling would continue. The physics behind this cooling process is fascinating. White dwarfs are supported against gravity, not by nuclear fusion, as in normal stars, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same energy state. This pressure remains constant, regardless of temperature, allowing white dwarfs to cool without contracting further. Initially, white dwarfs cool primarily through photon emission from their surface, radiating away their heat as light. But as they cool, their interiors crystallize, forming something akin to a giant diamond. This crystallization process releases additional heat, briefly slowing the cooling. Eventually, the entire star crystallizes, and cooling continues primarily through the emission of neutrinos, nearly massless particles that interact very weakly with matter. In the degenerate era, After all the stars have died, the sky would be mostly dark to human eyes. The white dwarfs would cool through yellow to orange to red and finally to infrared and microwave radiation, invisible to our biological vision. Eventually, after perhaps 10 to the power of 15 years, about 1,000 times longer than the current age of the universe, white dwarfs would cool to the background temperature of space, becoming what astronomers call black dwarfs. These black dwarfs would not be truly black in the sense of black holes. They would still contain matter, the highly compressed carbon and oxygen that once formed the core of a star, but they would be dark, cold, and inert, emitting no light and generating no heat, their atoms locked in a crystalline lattice similar to diamond. The formation of the first black dwarfs would mark a significant milestone in the history of the universe. It would signal the end of visible light production through natural means. The cosmos would grow increasingly dark, with only rare and temporary sources of illumination. Neutron stars would follow a similar cooling trajectory, though with important differences. These are the ultra-dense remnants of more massive stars, formed when stars between about 8 and 20 times the mass of our Sun explode as supernovae. In these catastrophic events, the core of the star collapses to extreme densities, squeezing protons and electrons together to form neutrons. A typical neutron star contains more mass than our Sun, compressed into a sphere just 20 kilometers across. Their density is almost incomprehensible, with a single teaspoon of neutron star material weighing billions of tons. Newly formed neutron stars are incredibly hot, with surface temperatures of millions of degrees Celsius, and they spin rapidly, sometimes hundreds of times per second. The interior of a neutron star represents some of the most extreme matter in the universe. Beneath the thin crust, perhaps a kilometer thick, lies a sea of neutrons behaving as a superfluid, a state of matter with zero viscosity. Deeper still, the pressure may be sufficient to break neutrons down into their constituent quarks, forming a quark-gluon plasma, unlike anything that naturally exists elsewhere in the modern cosmos. Like white dwarfs, neutron stars have no internal energy source after their formation. They cool by radiating away their heat, primarily through neutrino emission in their early lives, and then through photon emission as they age. However, their cooling process is more complex due to their exotic internal structure, which may include superfluids, superconductors, and other states of matter that exist only under extreme conditions. As neutron stars cool, they also slow their rotation. Many young neutron stars are pulsars, emitting beams of radiation that sweep across space like cosmic lighthouses as the star spins. These pulsars gradually lose rotational energy through magnetic braking and the emission of particles, causing them to spin more slowly over time. By the degenerate era, most pulsars would have slowed to the point where they no longer emit detectable pulses. Neutron stars would remain hotter than their surroundings for even longer than white dwarfs, perhaps for 10 to the power of 20 years. But eventually, they too would fade to black, becoming cold spheres of neutron matter drifting through the void. Black holes, the third type of stellar remnant, follow a different trajectory altogether. These form from stars more than 20 times the mass of our Sun, when their cores collapse so completely that not even neutron degeneracy pressure can halt the inward fall of matter. The result is an object so dense that it warps space-time to the point where nothing, not even light, can escape its gravitational pull. Unlike white dwarfs and neutron stars, black holes do not cool through thermal radiation. Their temperature, in a conventional sense, is meaningless, since no heat or light escapes the event horizon. However, through a quantum mechanical process called Hawking radiation, black holes do emit particles and gradually lose mass. This process is exceedingly slow for stellar mass black holes, taking unimaginable spans of time to have any significant effect. We will explore this process more deeply in a later chapter. During the degenerate era, these stellar remnants would drift through space, occasionally interacting through gravity. Most would be isolated, separated by vast distances as galaxies continue to expand due to dark energy. But some would remain bound in the cores of galaxies or in tight binary systems, their orbits gradually decaying through gravitational radiation. White dwarf binary systems would be particularly interesting during this era. When two white dwarfs orbit each other closely, they emit gravitational waves, ripples in spacetime that carry away orbital energy. This causes the white dwarfs to spiral gradually closer together. If they eventually merge, several outcomes are possible. If their combined mass exceeds about 1.4 times the mass of our Sun, known as the Chandrasekhar limit, the merger could trigger a catastrophic thermonuclear explosion, a Type Ia supernova. These would be rare but spectacular events in the otherwise dark degenerate era, briefly outshining all the remaining white dwarfs in a galaxy combined. If the merged white dwarf remains below the Chandrasekhar limit, it would simply form a larger white dwarf. If the mass exceeds the limit but conditions aren't right for a supernova, the white dwarf might collapse into a neutron star. And if the combined mass is high enough, it could even form a black hole. Similar mergers could occur between neutron stars or between neutron stars and black holes. These events would release enormous amounts of energy in the form of gravitational waves and, potentially, gamma-ray bursts. They would be like brief firecrackers in the cosmic darkness, momentarily lighting up small regions of the universe before fading away. In this epoch, the primary processes shaping the universe would be gravitational. With fusion extinguished and most normal matter locked away in degenerate objects, the elegant dance of gravity would continue to play out across the cosmos. Binaries would spiral together and merge. Remnants would be ejected from galaxies through gravitational interactions. The sparse halo of dark matter around galaxies would gradually lose energy through weak interactions, slowly contracting over enormous timescales. One might imagine that such a universe would be entirely dark, but there would still be occasional sources of light, brief flashes in the cosmic night. When two white dwarfs collide, they might trigger a supernova explosion, briefly illuminating their surroundings. When matter falls into a black hole, it would heat up and emit radiation before crossing the event horizon. When a black hole consumes a neutron star, gravitational waves would ripple through space-time, carrying energy away from the merger. These events would be increasingly rare as time progresses. In the early degenerate era, perhaps a few supernovae might still occur in each galaxy every million years. But as the eons pass, such events would become separated by billions or trillions of years, brief moments of light in a universe descending into darkness. Another source of activity in this era would come from proton decay. According to some theories in particle physics, protons, the building blocks of atomic nuclei, may not be truly stable. They might decay with a half-life of perhaps 10 to the power of 36 years, converting into lighter particles and releasing energy in the process. This theoretical decay would occur through processes predicted by grand unified theories, which suggest that at extremely high energies, the electromagnetic, weak, and strong nuclear forces merge into a single unified force. Through these processes, a proton might spontaneously transform into lighter particles, such as positrons and neutrinos, violating the conservation of baryon number that seems to hold in our current understanding of particle physics. If proton decay is real, then over the unimaginable timeframes of the degenerate era, even the seemingly stable matter in white dwarfs and neutron stars would gradually disappear. White dwarfs would slowly lose mass, their crystalline structures disrupted by the decay of their constituent protons. After 10 to the power of 37 years, half of all protons would have decayed, and the universe would be fundamentally altered on a subatomic level. The decay of protons would release small amounts of energy, providing a minimal heat source that might briefly delay the cooling of degenerate objects. But this would be a losing battle against the relentless expansion and cooling of the universe. During this era, any planets that survived the death of their parent stars would continue to orbit the stellar remnants, though in perpetual darkness and cold. These worlds would be frozen solid, their atmospheres condensed onto their surfaces as layers of exotic ices. Any complex molecules that might have indicated past life would slowly break down through natural radioactive processes and, eventually, proton decay. The moons and planets of our solar system, if they somehow survived the sun's red giant phase, would orbit the white dwarf remnant of our star in eternal night. Earth, if it still existed, would be a frozen ball of ice, its oceans solid, its atmosphere a thin layer of frozen nitrogen and oxygen on the surface. The chemical signatures of the life that once teemed on its surface would gradually degrade, erasing the evidence of our existence. The concept of habitable zones, regions around stars where liquid water can exist, would become meaningless. No world could support liquid water without an energy source. No photosynthesis could occur without light. No complex chemistry could proceed at temperatures near absolute zero. If any intelligence persisted into this era, it would not be biological as we understand it. The galaxies themselves would change during the degenerate era. Without star formation to sustain their spiral structures, galaxies like our Milky Way would lose their characteristic shape. The spiral arms, those beautiful cosmic pinwheels we see in telescopic images, are not solid structures, but waves of star formation moving through the galactic disk. Without new stars forming, these patterns would fade away. Additionally, over the span of trillions of years, gravitational interactions between stars and stellar remnants would alter galactic structure. These interactions tend to scatter objects into more three-dimensional distributions, converting flat spiral disks into spherical elliptical galaxies. The elegant spiral patterns that dominate our current cosmic landscape would give way to featureless elliptical blobs, and eventually to increasingly diffuse clouds of stellar remnants. Despite these changes, galaxy clusters would remain bound together by gravity, at least initially. The local group, which includes our Milky Way, Andromeda, and several smaller galaxies, would likely merge into a single massive elliptical galaxy. This combined galaxy would remain as a single entity, even as the universe around it continues to expand. However, beyond our local group, the accelerating expansion of the universe driven by dark energy would push other galaxy clusters beyond our cosmic horizon. By the time the degenerate era is well underway, observers in our galaxy would see only a handful of nearby galaxies, with the rest of the universe having receded beyond the observable limit. Within this isolated island of matter, gravitational processes would continue to operate. Stellar remnants would occasionally collide. Some would be ejected from the galaxy through three-body interactions. Others would gradually spiral toward the central supermassive black hole, feeding it with a slow but steady diet of matter and energy. This central black hole, already millions or billions of times more massive than our Sun, would continue to grow, albeit slowly. In the current universe, supermassive black holes grow primarily by consuming gas clouds. In the degenerate era, with gas long since depleted, they would grow by consuming stars and stellar remnants that wander too close. This growth would be glacial compared to the rapid accretion we observe today, but over the span of quintillions of years, it would still be significant. The universe will no longer shine, but it will still move. As we venture deeper into the cosmic timeline, we encounter a universe increasingly unlike our own. Throughout the degenerate era, the familiar structures of the cosmos, the galaxies that serve as the building blocks of large-scale structure, will themselves begin to unravel. This process, which we might call galactic dissolution, transforms the universe from a collection of distinct island universes to an increasingly diffuse soup of stellar remnants. In the universe we observe today, galaxies are held together by gravity. The combined mass of stars, gas, dust, and dark matter creates a gravitational well deep enough to prevent most objects from escaping. Stars orbit the galactic center just as planets orbit stars. Their paths dictated by the same gravitational laws that keep our feet planted firmly on Earth. But galaxies are not perfectly stable systems. Over long periods, gravitational interactions between stars can transfer energy in ways that alter their orbits. Sometimes, these interactions eject stars from galaxies entirely. This process, called gravitational ejection, is rare in our current universe, affecting perhaps one star in a million over the course of a billion years. But given enough time, it becomes a dominant force in galactic evolution. During the degenerate era, as white dwarfs and neutron stars drift through the darkened galaxies, these gravitational interactions will continue. When three or more stellar remnants pass close to one another, complex gravitational effects can transfer energy between them, accelerating one object while slowing others. Occasionally, these interactions provide enough energy for a stellar remnant to exceed the galaxy's escape velocity, sending it hurtling into intergalactic space. As this process continues over trillions upon trillions of years, galaxies will gradually lose mass. Each ejected object carries away a small portion of the galaxy's total gravitational binding energy, weakening the force that holds the remaining objects together. This makes subsequent ejections more likely, creating a feedback loop that accelerates the dissolution process. The mathematics of this dissolution follows what physicists call exponential decay. Initially, the process will be slow, with perhaps only a small percentage of stellar remnants ejected over the first trillion years. But as the galaxy weakens, the rate of ejection increases. By the time half the original mass has been lost, the process accelerates dramatically. The final stages of dissolution might occur relatively quickly, with the last 10% of objects dispersing in a small fraction of the total dissolution time. At the same time as this internal dissolution occurs, another force works to pull galaxies apart from the outside. Dark energy, the mysterious force driving the accelerating expansion of the universe, continues to stretch space itself. As space expands, the distance between galaxy clusters increases, reducing their gravitational influence on one another. In our current cosmic epoch, nearby galaxy clusters remain gravitationally bound despite cosmic expansion. The local group, which includes our Milky Way, the Andromeda Galaxy, and several dozen smaller galaxies, will eventually merge into a single massive galaxy due to their mutual gravitational attraction. But beyond our local group, the picture is very different. The Virgo cluster, the nearest large concentration of galaxies beyond our local group, is already receding from us at hundreds of kilometers per second. As dark energy continues to accelerate cosmic expansion, this recession velocity will increase. Eventually, perhaps a few 100 billion years from now, the Virgo cluster will cross a critical threshold, receding faster than the speed of light relative to our position. This does not violate Einstein's special relativity because it is space itself that is expanding, carrying galaxies along with it, rather than the galaxies moving through space at superluminal velocities. But the effect is the same. A cosmic horizon forms beyond which we can never send or receive signals again. One by one, distant galaxy clusters will slip beyond this horizon. The observable universe will shrink, not because our instruments become less powerful, but because fewer and fewer objects remain close enough for their light or any other form of information to ever reach us. By the time the degenerate era is well underway, perhaps 100 billion years from now, observers in our local group would see only darkness beyond our consolidated galactic island. The rest of the universe would have receded beyond detection, each galaxy cluster becoming an isolated island in an expanding sea of emptiness. Within these isolated clusters, gravitational interactions would continue. The largest galaxies would gradually consume smaller ones. Stellar remnants would be ejected into intergalactic space. The central supermassive black holes would grow slowly by consuming objects that wander too close. But no new material would enter the cluster from outside, and no information about the fate of other clusters would ever arrive. This isolation is profound. In the current universe, we can observe galaxies billions of light years away because their light has had the entire age of the universe to reach us. But as cosmic expansion accelerates, even light emitted now from distant galaxies may never reach us, and light we emit now may never reach them. The universe fragments into causally disconnected regions, each forever ignorant of the fate of the others. Within our isolated local group, now merged into a single galaxy, the process of dissolution would continue. Over timescales of quintillions of years, gravitational interactions would eject more and more stellar remnants. The galaxy would puff up, becoming increasingly diffuse as objects spread into wider and more eccentric orbits. The central supermassive black hole would exert its influence, gradually pulling in stellar remnants that pass too close. Each consumed object would make the black hole slightly more massive, slightly extending its gravitational reach. But this process would be exceedingly slow, with perhaps only a small percentage of remnants finding their way into the black hole over the entire degenerate era. Even dark matter, the invisible substance that makes up roughly 85% of the matter in our universe, would participate in this dissolution. Dark matter particles, whatever they may be, interact primarily through gravity. As the galaxy disperses, the dark matter halo surrounding it would also spread out, its density dropping as its constituent particles follow the changing gravitational potential. If dark matter consists of weakly interacting massive particles, as many physicists suspect, these particles might occasionally annihilate when they collide, converting their mass to energy and further depleting the dark matter content of the universe. This process, like proton decay, would occur over vast timescales, gradually eroding the invisible scaffolding that helped shape cosmic structure. By the time a quadrillion years have passed, approximately 100,000 times the current age of the universe, the once dense, organized galaxies would be largely unrecognizable. The majority of stellar remnants would have been ejected into intergalactic space, forming a diffuse cloud extending far beyond the original galactic boundaries. What remained would be a loose association of objects orbiting the central black hole at great distances, their paths taking them far from the galactic center before returning. This process represents a kind of heat death on the galactic scale. Organized, tightly bound systems give way to diffuse, disordered ones. The gravitational potential energy that once held galaxies together dissipates, converted to the kinetic energy of ejected objects. The entropy, or disorder, of the system increases, following the same thermodynamic laws that govern much simpler physical systems. For any hypothetical observers persisting in this distant era, the night sky would be nearly empty. The few visible objects would be relatively nearby white dwarfs, now cooled to black dwarfs, detectable only by their gravitational influence or by artificial illumination. The dense star fields that fill our current night sky would be gone, replaced by almost perfect blackness. As we consider this process of galactic dissolution, it's worth noting that we are describing the most likely outcome based on our current understanding of physics. If dark energy behaves differently than we expect, the picture could change. If dark energy weakens over time, cosmic expansion might slow, allowing gravity to reassert its influence on the largest scales. In this scenario, galaxy clusters might remain bound together for much longer, or even begin to fall back toward one another in a big crunch scenario. Conversely, if dark energy strengthens over time, cosmic expansion could accelerate even faster than currently predicted. In an extreme case, this could lead to a big rip, where the fabric of space-time tears apart, ripping first galaxy clusters, then individual galaxies, then solar systems, and ultimately atoms themselves. But current observations suggest that dark energy remains constant over time, making the gradual dissolution scenario more likely. The dissolution of galaxies represents another key transition in cosmic history. Just as the era of star formation gave way to the degenerate era, the era of galaxies gives way to an increasingly homogeneous universe. The distinct structures that have characterized the cosmos since soon after the Big Bang fade away, leaving a universe that is both simpler and emptier. In this process, we see a pattern that repeats throughout cosmic evolution: the transition from complexity to simplicity, from order to disorder, from concentrated energy to diffuse energy. The same fundamental laws that built the intricate structures of our universe, from atoms to stars to galaxies, also ensure their eventual dissolution. But this process unfolds with incredible slowness. The galaxies we see today, including our own Milky Way, will maintain their general structure for trillions of years to come. The dissolution we describe occurs on timescales so vast that they dwarf the current age of the universe. A human lifetime, or even the entire span of our species' existence, registers as less than an eye blink on this cosmic clock. As the dissolution continues, the remaining stellar remnants drift farther apart. Encounters between objects become increasingly rare. The universe grows quieter, with fewer and fewer events to break the darkness. The gravitational waves that ripple through space-time when massive objects interact become separated by eons of silence. Eventually, after perhaps 10 to the power of 20 years, the dissolution would be nearly complete. The galaxy that once contained hundreds of billions of stars would be reduced to a central, supermassive black hole surrounded by a sparse cloud of stellar remnants, their orbits taking them so far from the center that they might not return for trillions of years. The vast majority of objects that once comprised the galaxy would be scattered throughout intergalactic space, drifting alone through the void. Each galaxy, once bound by gravity, drifts alone into the dark. After the galaxies have dissolved, after the stellar remnants have cooled to darkness, after matter itself has begun to decay, the universe enters perhaps its strangest phase yet. Beginning roughly 10 to the power of 40 years from now, the cosmos becomes dominated by objects that are, in a sense, holes in the fabric of reality itself. This is the black hole era, when the darkest entities in the universe become the final repositories of mass and energy. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape once it passes the event horizon. They form when matter is compressed beyond a critical density, causing space-time to curve so extremely that it creates a one-way membrane around the compressed mass. Anything can enter, but nothing can leave, at least through conventional means. In our current universe, black holes come in several varieties. Stellar black holes form from the collapsed cores of massive stars, typically containing between 5 and several dozen times the mass of our Sun. Intermediate black holes, with masses hundreds to thousands of times that of our Sun, may form through the merger of smaller black holes or the collapse of exceptionally massive stars. And supermassive black holes with masses millions to billions of times that of our Sun sit at the centers of most galaxies, including our own Milky Way. During the black hole era, these will be the only significant gravitational structures remaining in the universe. The bright stars, white dwarfs, neutron stars, and even planets will have long since disappeared through various processes. Only black holes with their ability to lock away matter for almost unimaginable durations will persist. But even black holes are not eternal. Through a quantum mechanical process, discovered by Stephen Hawking in the 1970s, black holes actually emit radiation and slowly lose mass. This Hawking radiation, as it is called, comes from virtual particle pairs that form spontaneously near the event horizon due to quantum fluctuations in the vacuum. When one particle of the pair falls into the black hole and the other escapes, the black hole effectively loses mass. This process is excruciatingly slow for large black holes. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate completely, far longer than the current age of the universe. More massive black holes would take even longer, with the timescale proportional to the cube of the mass. A supermassive black hole, with the mass of the one at the center of our Milky Way, Sagittarius A star, would take roughly 10 to the power of 100 years to disappear. Because of this relationship between mass and evaporation time, larger black holes outlive smaller ones. During the early phase of the black hole era, the stellar mass black holes will be the first to vanish, popping out of existence one by one as they radiate away their final particles. The intermediate mass black holes will follow. And finally, after timescales that defy human comprehension, the supermassive black holes will begin to noticeably shrink. As a black hole evaporates, its temperature and luminosity actually increase. A solar mass black hole has a temperature of only about 60 nanokelvin, making it colder than the cosmic microwave background radiation in our current universe. It emits an insignificant amount of energy, far less than the weakest radio wave. But as the black hole loses mass, its temperature rises inversely with its mass. In its final moments, a black hole reaches tremendous temperatures, briefly blazing with a fierce light before disappearing entirely. These final flashes will be the last significant energy releases in the universe, but they will illuminate nothing, for there will be nothing left to see and no one left to watch. The once vibrant cosmos will have become an almost perfect vacuum, with only the most minute particles scattered at unimaginable distances from one another. During the black hole era, matter exists primarily in one of two states, locked away inside black holes or scattered as fundamental particles through the void. The universe becomes extraordinarily simple compared to our current complex cosmos. No atoms, no molecules, no chemical reactions, no stars, no galaxies, no complex structures of any kind. Just black holes and elemental particles drifting through an ever-expanding, ever-cooling space. Occasionally, a particle might fall into a black hole, ever so slightly increasing its mass and delaying its evaporation. But these events become increasingly rare as cosmic expansion continues to dilute the particle density of the universe. Each black hole sits alone in an immense bubble of near-perfect vacuum, slowly radiating away its mass energy with virtually no new input. The duration of the black hole era dwarfs all previous cosmic epochs combined. Where the stelliferous era, the age of stars in which we live, lasts for perhaps 100 trillion years, and the degenerate era might stretch for a quadrillion years beyond that, the black hole era persists for up to 10 to the power of 100 years. This is such a vast time span that it defies meaningful comparison. It is longer than it would take to count every atom in the observable universe, one by one, at a rate of 1 atom per century. During this unimaginable stretch of time, black holes reign as the ultimate physical structures. They represent the universe's last effort to maintain any form of complex entity, the final stand against the relentless increase of entropy. But it is a losing battle. One by one, they fade away, returning their hoarded mass energy to the cosmos as radiation. As black holes evaporate, they follow an interesting progression. For most of their lives, they lose mass very slowly, with little noticeable change over vast periods. But the evaporation accelerates as the black hole shrinks. The smaller the black hole, the hotter its temperature, and the more quickly it radiates energy. This creates a runaway effect in the final stages of evaporation. A black hole with the mass of our Sun would spend the vast majority of its 10 to the power of 67-year lifespan with almost no noticeable change. But in its final year, it would begin to glow visibly. In its final second, it would reach temperatures of billions of degrees, unleashing an explosion of elementary particles before vanishing completely. The physics of the final moments of black hole evaporation remains somewhat uncertain. Some theories suggest that black holes might leave behind a remnant, a tiny particle containing a fraction of the original black hole's mass. Others propose that the information apparently lost when matter falls into a black hole might be preserved in subtle correlations in the Hawking radiation, maintaining the principle of information conservation that is fundamental to quantum mechanics. What is certain is that black holes cannot last forever in a universe dominated by dark energy. As they radiate away their mass, no matter how slowly, they will eventually disappear, leaving behind either nothing at all or perhaps the most elemental particles permitted by the laws of physics. The fate of these particles, whether remnants of black holes or the sparse matter that never fell into one, depends on whether protons decay, as discussed in a previous chapter. If protons and other elementary particles are truly stable, they might persist indefinitely, drifting through an otherwise empty cosmos. If not, even they will eventually vanish, converting to radiation through decay processes predicted by some theories in particle physics. As we contemplate the black hole era, we are forced to reconsider our understanding of time itself. The timescales involved are so vast that they make a mockery of our usual temporal references. A billion years, already far beyond human comprehension, becomes an insignificant moment. A trillion years passes without meaningful change. Time stretches toward a kind of eternity, albeit one that still has an ending. In such a universe, the concept of events becomes almost meaningless. When the average time between significant occurrences exceeds the current age of the universe by factors of trillions or more, can we really speak of a sequence of happenings? The universe approaches a state of near-perfect stasis, changing so slowly that change itself loses significance. And yet, the laws of thermodynamics continue their inexorable work. Entropy increases as organized forms of energy convert to disorganized ones. The energy locked in the mass of black holes gradually spreads out as Hawking radiation, becoming more diffuse and less useful for doing work. The universe continues its one-way journey from a state of low entropy to a state of high entropy, from order to disorder, from complexity to simplicity. The black hole era represents the universe's long, slow exhale. The furious activity of the early cosmos, the steady burning of the stelliferous era, the quiet cooling of the degenerate era, all give way to this longest of cosmic phases, where change occurs at a glacial pace and the universe gradually lets go of its final structured forms. It is tempting to view this era as a kind of cosmic twilight, the dim afterglow of a universe winding down. But we might also see it as a testament to the remarkable persistence of organization in a universe governed by entropy. That complex structures like black holes can endure for such unimaginable timeframes speaks to the deep relationship between gravity, quantum mechanics, and thermodynamics. Black holes are, in a sense, the universe's most efficient batteries, storing energy in a form that dissipates more slowly than any other known structure. They represent the cosmos's final resistance to the heat death that looms in its future. And their gradual evaporation is not so much a surrender to disorder as it is the slowest possible release of energy, stretched across timeframes that make the current age of the universe seem like less than an eye blink. Throughout the black hole era, cosmic expansion continues, driven by dark energy. The already vast distances between objects grow ever larger. Any black holes that formed from the remnants of a single galaxy find themselves separated by distances measured in millions or billions of light years. And this separation increases with time. The universe becomes increasingly diffuse, with its remaining energy spread across an ever-expanding volume. This expansion further isolates each black hole, making it even less likely that they might interact or capture new particles. Each sits in its own vast bubble of near-perfect vacuum, alone with its slowly radiating event horizon, as close to eternal as any physical object can be, yet still ultimately ephemeral. If any intelligence, natural or artificial, somehow managed to persist into this era, it would face a stark reality. Energy, the currency of all activity, would be extraordinarily scarce. The only significant sources would be the Hawking radiation from black holes, a pitifully feeble trickle for most of their lifespans. Computation, thought, action, all the activities we associate with living systems, would be severely constrained by this energy poverty. An entity might position itself near a black hole, harvesting its radiation for the energy needed to maintain its processes, but it would be gathering droplets from the slowest of faucets, extracting the barest minimum of energy from an object designed by nature to hold onto it as long as possible. Whether complex organization of any kind could persist under such constraints remains an open question. As the black hole era progresses through its almost incomprehensible time span, the universe grows ever darker, cooler, and emptier. The already sparse matter density drops as protons potentially decay and black holes gradually evaporate. The cosmos approaches the state that physicists call the heat death, where all energy is distributed uniformly and no further work can be extracted. But before that final state arrives, the last black holes must complete their evaporation. The final moments of the ultimate black hole, likely one of the supermassive giants from a galactic center, would occur approximately 10 to the power of 100 years from now. In a brief but intense flash, the last structured object in the universe would convert its remaining mass to energy and vanish. This final burst of radiation would spread outward through the void, gradually redshifting as it traveled through the still expanding cosmos until it became indistinguishable from the background. The only things that remain are the hungriest shadows of all. In the profound darkness of the black hole era, a subtle process unfolds that will ultimately bring even these mighty cosmic objects to their end. This process, called Hawking radiation, represents one of the most remarkable intersections of quantum mechanics and general relativity, the two great pillars of modern physics. It is through this quiet, persistent phenomenon that the universe's final structured objects will eventually dissolve into the void. Hawking radiation is named after the physicist Stephen Hawking, who predicted its existence in 1974. The mechanism behind it reveals the strange nature of the quantum vacuum and the seemingly solid boundary we call a black hole's event horizon. In quantum field theory, empty space is not truly empty. It seethes with virtual particles that pop into existence in pairs, only to annihilate each other almost immediately and disappear back into the vacuum. These particles and antiparticles materialize briefly due to quantum fluctuations, borrowing energy from the vacuum as permitted by Heisenberg's uncertainty principle, before repaying this energy debt by recombining. Near a black hole's event horizon, this quantum process takes on cosmic significance. When a pair of virtual particles forms close to the event horizon, an extraordinary possibility arises. One particle may fall into the black hole while the other escapes into space. The infalling particle, which possesses negative energy relative to the universe outside the black hole, reduces the black hole's mass by a tiny amount. Meanwhile, the escaping particle, which has positive energy, appears to an outside observer as radiation emitted from the black hole. This radiation is not drawn from the material that originally formed the black hole. Rather, It represents energy extracted from the gravitational field of the black hole itself. Each emitted particle carries away a minuscule portion of the black hole's mass energy, causing the black hole to shrink almost imperceptibly. For large black holes, this process occurs with extreme slowness. A black hole with the mass of our Sun emits Hawking radiation, with a temperature of only about 60 nanokelvin, far colder than the cosmic microwave background radiation in our current universe. At this temperature, the energy loss is so minimal that the black hole would take approximately 10 to the power of 67 years to evaporate completely. The equation governing this evaporation time reveals a startling relationship. The lifetime of a black hole is proportional to the cube of its mass. Double the mass, and the lifetime increases eightfold. This relationship means that more massive black holes persist far longer than smaller ones. A supermassive black hole with 1 billion solar masses might endure for up to 10 to the power of 100 years, a time span so vast that it defies intuitive understanding. As a black hole loses mass through Hawking radiation, its surface area decreases, and the curvature of space-time at its event horizon becomes more extreme. This increased curvature leads to a stronger gravitational field in the immediate vicinity of the horizon, which in turn affects the production of virtual particle pairs. The rate of radiation emission gradually increases, causing the black hole to lose mass at an accelerating pace. This creates an interesting progression in the life cycle of a black hole. For the overwhelming majority of its existence, the black hole emits radiation at such a low rate that it seems almost unchanged for incomprehensibly long periods. But as it shrinks past a critical point, the evaporation begins to accelerate noticeably. The black hole grows hotter, emitting more energetic radiation at a higher rate, which in turn causes it to shrink faster, growing hotter still. In the final stages, this process becomes explosive. A black hole approaching the end of its life would shine with increasing brightness, its temperature rising to billions and then trillions of degrees. In its last moments, the black hole would release an enormous burst of high-energy radiation, a final flash in the darkness of the far future universe, before disappearing completely. The nature of this radiation changes throughout the black hole's lifetime. Initially, when the black hole is large and its temperature extremely low, the radiation consists primarily of massless particles like photons and gravitons, the theoretical particles that carry the gravitational force. These particles can be created with very little energy, making them the predominant form of Hawking radiation from cool black holes. As the black hole shrinks and heats up, it begins to emit more massive particles. Neutrinos appear in the radiation spectrum, followed by electrons and positrons. In its final moments, when the black hole's temperature soars to unimaginable heights, it may emit the full spectrum of elementary particles, perhaps even particles that can only be created at energies far beyond what our current particle accelerators can achieve. This progression reveals something profound about black holes. Though we think of them as objects that trap light and matter, preventing anything from escaping, Hawking radiation means that black holes actually do communicate information about themselves to the outside universe. The temperature and spectrum of the radiation depend on the black hole's mass, angular momentum, and charge, encoding these properties in the particles emitted. Yet this leads to an apparent paradox. Quantum mechanics insists that information cannot be destroyed, only transformed. But a black hole seems to destroy the information contained in the matter that falls into it, returning only thermal radiation that carries no details about the original infalling material. This conundrum, known as the black hole information paradox, has puzzled physicists for decades and remains only partially resolved. Some theories suggest that the information might be preserved in subtle correlations between the particles of Hawking radiation, encrypted in a complex code that could, in principle, be deciphered to reconstruct the details of everything that ever fell into the black hole. Others propose that the information might be stored in a sort of holographic imprint on the event horizon itself. Still others suggest more exotic possibilities, such as the information escaping into other universes through wormholes within the black hole. Whatever the resolution, the ultimate fate of black holes seems clear. Through Hawking radiation, they slowly return the mass energy they have accumulated to the wider universe, converting organized matter into disorganized radiation. This process represents entropy increase in its purest form, the transformation of highly concentrated energy into a diffuse, spread-out state. In the far distant future, after most other processes have ceased, the evaporation of black holes through Hawking radiation continues. The smaller stellar mass black holes go first, popping out of existence one by one, their brief final flares momentarily illuminating the darkness before fading away. The intermediate mass black holes follow, and finally, after timeframes that make the current age of the universe seem like less than a heartbeat, the supermassive black holes begin to noticeably shrink. Each evaporation event releases the mass energy locked within the black hole, converting it primarily to electromagnetic radiation and neutrinos. This energy travels outward through the increasingly tenuous vacuum, gradually redshifting due to cosmic expansion until it becomes indistinguishable from the background. The fact that black holes are not truly eternal objects, but instead have finite, if extraordinarily long lifespans, has profound implications for the ultimate fate of the universe. No structure, no matter how stable it might seem, can persist indefinitely. Even the darkest, most tightly bound configurations of mass energy must eventually dissolve, returning to the simplest, most elemental forms. For much of the 20th century, physicists believed that black holes represented a one-way street, an irreversible compression of matter from which nothing could ever return. Hawking's discovery changed this view fundamentally. Black holes are not cosmic sinkholes, permanently removing mass energy from the active universe, but rather the longest-lived batteries imaginable, storing energy for almost unimaginable durations before gradually releasing it back to the cosmos. This reframes our understanding of cosmic evolution. Rather than the universe dividing into active and inactive regions, with an ever-increasing portion of its mass energy locked away in black holes, we now see that all energy eventually returns to the broader cosmos. The black holes are not an end state, but merely the longest chapter in a continuing story. As we contemplate these processes, unfolding over timeframes that strain our capacity for comprehension, we might wonder about the ultimate significance of such distant events. The evaporation of the last black hole will occur tens of orders of magnitude further in the future than our current distance from the Big Bang. Any intelligence that might witness these final moments would be so remote from us in time that the entirety of human existence would appear to them as we perceive the briefest subatomic interactions. And yet, these far future events connect directly to our present through the unbroken chain of physical law. The same principles that govern the behavior of matter and energy in our everyday world, extended to their logical conclusions across the vast sweep of cosmic time, predict the eventual evaporation of black holes through Hawking radiation. Our theories, developed in the brief moment of cosmic history we occupy, reach forward to describe the universe's most distant future. In a sense, understanding the ultimate fate of black holes allows us to glimpse the full arc of cosmic history, from the hot, dense beginning to the cold, diffuse end. We see that the universe follows a trajectory from simplicity through complexity and back to simplicity again. The early universe was simple due to the extreme conditions that limited the possible forms matter and energy could take. The middle period in which we live permits extraordinary complexity as matter organizes into atoms, molecules, stars, planets, and perhaps even life. And the far future universe returns to simplicity as complex structures break down and energy spreads out evenly through an ever-expanding space. The evaporation of black holes represents the final significant phase change in this great cosmic trajectory. After the stars have burned out, after the stellar remnants have cooled, after protons have potentially decayed, the slow evaporation of black holes through Hawking radiation continues, the last structured process in a universe winding down toward heat death. Imagine, if you can, witnessing the final moments of the last black hole. After existing for a time span that makes the current age of the universe seem insignificant, the black hole has shrunk to a tiny fraction of its original size. Its temperature has risen to trillions of degrees. In the last second of its existence, it shines with a brightness that would outshine our entire galaxy, a final defiant flare against the encroaching darkness. And then, In a burst of elementary particles, it vanishes completely, leaving behind only the radiation rapidly dispersing into the void. This final flash marks the end of structured objects in the universe. After this point, only free elementary particles and radiation remain, drifting through an increasingly diffuse vacuum as cosmic expansion continues to stretch space ever thinner. No further significant events occur, no new structures form. The universe has reached a state of near-perfect equilibrium, with energy distributed so evenly that no useful work can be extracted. Even darkness is not forever. The last giants dissolve into the void. After the last black hole has evaporated, after the final burst of Hawking radiation has spread through the vastness of space, the universe enters its ultimate phase, a state that physicists call the heat death. This is not death by heat in the conventional sense, but rather a state where all energy has spread out as evenly as possible, where no significant temperature differences exist, and where no useful work can be extracted from the system. It is a universe of perfect equilibrium, the final destination of a cosmic journey that began with the extraordinary disequilibrium of the Big Bang. To understand the heat death, we must consider the concept of entropy, often described as a measure of disorder in a system. But entropy is more precisely understood as a measure of energy dispersal or distribution. High entropy states are those where energy is spread out widely and evenly, while low entropy states feature concentrated energy with significant differences in distribution. The laws of thermodynamics tell us that in any isolated system, entropy tends to increase over time. Order gives way to disorder. Concentrated energy disperses. Hot objects cool and cold objects warm until thermal equilibrium is reached. This direction of change, from low entropy to high entropy, gives time its arrow, distinguishing the past from the future in our everyday experience. Our universe began in a state of remarkably low entropy. The Big Bang, contrary to what its name might suggest, was not a chaotic explosion, but an extraordinarily organized event. Energy was distributed very unevenly, creating the potential for all the complex processes that would follow. This initial state was so improbable, so special, that explaining it remains one of the great challenges in cosmology. From this highly organized beginning, the universe has been evolving toward ever higher entropy states. Stars burn, converting the concentrated energy in their nuclear fuel to more diffuse radiation. Living organisms maintain their internal order only by increasing the entropy of their surroundings. Every process that occurs naturally, from the brewing of a cup of tea to the explosion of a supernova, increases the total entropy of the universe. Given enough time, this relentless increase in entropy leads to the heat death, a state where entropy has reached its maximum possible value. In this state, energy is distributed as uniformly as possible throughout space. No significant temperature differences exist to drive heat engines. No concentration of matter exists to collapse gravitationally. No processes occur that could be harnessed to perform work. This final state of the universe would be one of thin, cold, diffuse radiation, spread almost perfectly evenly through an immense and ever-expanding space. The temperature would approach, but never quite reach, absolute zero, hovering just slightly above it due to the residual energy from all the processes that came before. This temperature would be uniform throughout the observable universe, with no warmer or cooler regions to create energy gradients. Matter in the conventional sense would no longer exist. If protons are unstable, as some theories suggest, then they would have decayed long ago, converting to lighter particles and radiation. Even if protons are stable, they would be scattered so widely by cosmic expansion that interactions between them would be essentially non-existent. Each elementary particle would drift alone through the void, never encountering another for the rest of time. The electromagnetic radiation that once streamed from countless stars would have redshifted to such extreme wavelengths that individual photons would be separated by vast distances. The cosmic microwave background, already cool in our era at just 2.7 Kelvin, would have redshifted to nearly absolute zero, its photons stretched to wavelengths larger than the current observable universe. Gravitational waves, ripples in space-time generated by the movement of massive objects, would have similarly stretched and weakened. The last significant gravitational waves would have been produced by the final black hole mergers, or the asymmetrical evaporation of the last black holes. These waves would propagate through the empty cosmos, gradually diminishing in strength as they traverse the expanding space. Neutrinos, nearly massless particles that interact only weakly with other forms of matter, would constitute a significant portion of the particle content of this future universe. Produced in abundance during the stelliferous era and released during the final evaporation of black holes, these ghost-like particles would travel unimpeded through the vacuum, so rarely interacting that they might as well be completely isolated. In this state of maximum entropy, time in a meaningful sense almost ceases to exist. Change becomes so minimal, so insignificant, that the universe approaches a kind of stasis. Without significant events to mark the passage of time, without processes that proceed in one direction rather than another, time loses its arrow. The distinction between past and future blurs, not because time stops flowing, but because nothing happens that could define its direction. The heat death is sometimes called the Big Freeze, a reference to the extraordinarily low temperatures that would prevail. But this name might be misleading, as freezing implies a phase change, a transition from one state of matter to another. In the heat-death universe, no such transitions occur. There is only the slow, gradual approach toward absolute zero, never quite reaching it due to the residual energy permeating space. Another name occasionally used is the Big Chill, which perhaps better captures the gradual nature of this ultimate fate. The universe does not suddenly freeze, but rather continues to cool, asymptotically approaching absolute zero without ever quite reaching it, just as entropy approaches but never quite achieves its theoretical maximum value. The timescale on which the heat death occurs depends on several factors, including the future behavior of dark energy and whether protons decay. If dark energy remains constant and protons do decay, the heat death might begin after approximately 10 to the power of 100 years, following the evaporation of the last supermassive black hole. If protons are stable, the timeline stretches even further, with elementary particles persisting indefinitely in an ever more diffuse state. But regardless of these details, the character of the heat death remains the same, a state of near-perfect equilibrium, with energy distributed as evenly as possible throughout an expanding space. The universe becomes, in essence, a thin, cold soup of elementary particles and low-energy radiation, stretched across an unimaginably vast volume. One might wonder whether anything could survive in such a state, whether any form of complexity or organization could persist against the overwhelming tide of entropy. The prospects seem bleak. Conventional life, as we understand it, requires significant energy gradients to maintain its internal organization. Biological processes depend on chemical reactions that become impossible at temperatures approaching absolute zero. Even the simplest organisms we know would find no usable energy sources in the heat-death universe. Technological systems, however advanced, would face similar challenges. Computation requires energy to distinguish between information states. As energy becomes increasingly diffuse, the ability to process information diminishes. Eventually, the energy required to perform even the simplest calculation would be spread across such vast distances that it could not be gathered in useful concentrations. Some physicists have speculated about the possibility of intelligence adapting to these increasingly hostile conditions. As available energy decreases, a sufficiently advanced entity might slow its processing speed, thinking ever more slowly to conserve energy. By reducing its operating temperature and extending the time between computational steps, such an entity might stretch its subjective existence far beyond what seems possible. But there are fundamental limits to this approach. As the universe continues to expand and cool, the energy available for computation decreases without bound. Even with perfect efficiency, an entity would eventually face a choice between ceasing operations entirely or stretching the time between thoughts to such extremes that meaningful consciousness would be lost. In the heat-death universe, the very concept of existence takes on a different character. With no significant events, no meaningful interactions, and no energy gradients to drive change, existence becomes a kind of eternal, unchanging present. The universe neither develops nor decays in any significant way, but simply persists in a state so close to perfect equilibrium that deviations are immeasurably small. This ultimate fate represents the completion of a great cosmic cycle from simplicity through complexity and back to simplicity. The universe began in a simple but highly organized state, with energy concentrated and entropy low. It evolved through a period of increasing complexity, with the formation of subatomic particles, atoms, molecules, stars, galaxies, and perhaps even life. And it ends in a simple but highly disorganized state, with energy dispersed and entropy high. The heat death does not mark the end of the universe in an absolute sense. Space continues to exist. Time continues to flow. The elementary particles and radiation that constitute the cosmos continue to persist. But the universe becomes functionally dead, incapable of supporting complex structures or meaningful processes. It reaches a state of perfect quietude, a cosmos without events. This vision of the far future might seem bleak, a universe winding down into eternal stagnation. But there is a certain austere beauty in the heat death, a simplicity and equality that contrasts with the hierarchical, varied universe we inhabit. In the heat death, all energy has the same status. All locations in space are functionally identical. The distinctions that define our current reality, the boundaries between objects, the hierarchies of structure, the centers and peripheries, all dissolve into a homogeneous whole. Moreover, the heat death represents the fulfillment of the laws of physics as we currently understand them. It is not an aberration or a failure, but the natural and inevitable consequence of principles that have operated since the universe began. The increase of entropy, the tendency of energy to disperse, the expansion of space, all point toward this ultimate state of equilibrium. In contemplating the heat death, we confront the deepest questions about time, purpose, and the nature of existence. We are forced to consider whether meaning requires change, whether value can exist in a static state, whether the journey matters more than the destination. These are not just scientific questions, but philosophical ones, touching on our understanding of ourselves and our place in the cosmic story. The heat death also highlights the extraordinary specialness of our current cosmic epoch. We live in a time when energy gradients still exist, when complexity is possible, when stars shine and chemistry operates and life can evolve. This middle period of cosmic history, between the simple order of the beginning and the simple disorder of the end, possesses a richness and potential that makes it unique in the vast sweep of time. Perhaps most remarkably, we exist at a moment when the universe has developed the capacity to understand itself. Through science, through observation and theory, we piece together the story of cosmic evolution, from the Big Bang to the heat death and beyond. We, complex structures composed of atoms that were forged in stars, contemplate the beginning and end of all things. In our brief moment of existence, we glimpse the entire arc of cosmic history. As we imagine the heat death with its perfectly dispersed energy and maximal entropy, we might wonder whether this truly represents the final chapter in the cosmic story. Are there processes, currently unknown to physics, that might reverse the tide of entropy or create new pockets of order in the equilibrium state? Might new universes emerge from the void, restarting the cycle of cosmic evolution? These possibilities, while speculative, remind us that our understanding remains incomplete, that the universe may hold surprises beyond our current theories. For now, our best understanding points toward the heat death as the ultimate fate of our universe. After all the stars have burned out, after all the black holes have evaporated, after all structures have dissolved and all energy has dispersed, the cosmos approaches a state of perfect stillness. Entropy reaches its maximum. Energy achieves its most uniform distribution. The universe becomes quiet. As we contemplate the heat death of the universe, that state of perfect equilibrium where all energy has dispersed and entropy has reached its maximum, a question naturally arises. Is this truly the end? Or might there be processes, perhaps operating on scales or through mechanisms currently beyond our understanding, that could restart the cosmic cycle, creating new complexity from the ashes of the old? Throughout human history, many cultures have embraced cyclical models of the universe, where creation and destruction alternate in an eternal pattern. From the Hindu concept of cosmic cycles spanning billions of years, to the Norse Ragnarok, followed by rebirth, The idea that endings lead to new beginnings has deep resonance in human thought. But what does modern cosmology say about the possibility of a universal reboot? Several scientific theories propose mechanisms through which our universe might not end in eternal stasis, but instead seed the formation of new universes or regenerate itself. Let us explore these possibilities, remembering that while they are grounded in serious theoretical physics, they remain speculative and in many cases untestable with current technology. The Big Bounce is perhaps the most direct reversal of the heat-death scenario. In this model, the current expansion of the universe eventually halts and reverses, leading to a cosmic contraction or big crunch. As all matter and energy collapse back toward a singularity similar to the Big Bang, quantum effects might prevent a true singularity from forming. Instead, the universe might bounce, expanding outward again in a new Big Bang. For decades, the Big Bounce seemed increasingly unlikely as observations indicated an accelerating cosmic expansion driven by dark energy. If this acceleration continues indefinitely, the universe will never recollapse, but instead expand forever, making a bounce impossible. However, some theories suggest that dark energy might not be constant. If it weakens over time, or even changes sign, becoming attractive rather than repulsive, a future recollapse remains possible. More exotic bounce models propose that quantum effects near the Big Crunch might violate the classical laws of general relativity, forcing a bounce even without a reversal of cosmic expansion. These models draw on various approaches to quantum gravity, the still developing theory that would unite quantum mechanics with Einstein's theory of gravity. The cyclic or ekpyrotic universe model, developed by Paul Steinhardt, Neil Turok, and others, offers a different approach to cosmic rebirth. In this scenario, our three-dimensional universe exists as a brane, a membrane-like structure in a higher dimensional space. Our universe might periodically collide with another brane, with each collision generating a new Big Bang. The current expansion, heat death, and dissolution of structure would simply be one phase in an endless cycle of collisions and rebirths. This model has the intriguing feature of potentially resolving the low entropy problem of the early universe. Rather than requiring an unexplained, initially low entropy state, the ekpyrotic model suggests that each collision naturally produces the conditions we associate with the Big Bang. However, it relies on string theory and extra dimensions, concepts that, while mathematically consistent, have yet to receive experimental confirmation. Conformal cyclic cosmology, proposed by mathematical physicist Roger Penrose, offers yet another possibility for universal renewal. Penrose notes a curious mathematical similarity between the extremely hot, dense early universe and the extremely cold, diffuse late universe after heat death. Both states, despite their physical differences, lack a meaningful scale, with elementary particles behaving essentially as massless entities without a characteristic size. This similarity allows Penrose to propose that the remote future of one universe could, through a conformal transformation preserving angles but not distances, become the Big Bang of another. In this view, the cycle of universes continues indefinitely, with the heat death of each universe becoming the hot, dense beginning of the next, though without any causal memory passing between cycles. Eternal inflation provides another framework for cosmic renewal, though one that generates multiple universes rather than cycling a single one. In this model, first proposed by André Linde and others, the very early universe underwent a period of exponential expansion, driven by the energy of a quantum field in a false vacuum state. While this inflation ended in our observable universe, allowing normal cosmic evolution to proceed, it continues in other regions, eternally generating new bubble universes with potentially different physical laws. In the eternal inflation scenario, our universe is just one bubble in an infinitely branching multiverse. Even after our universe reaches heat death, the broader process of inflation continues, spawning new universes forever. While we cannot access these other universes or survive the death of our own, the creative process of cosmos generation never ceases. Quantum fluctuations offer perhaps the most speculative path to universal renewal. In quantum mechanics, the vacuum is never truly empty, but instead seethes with virtual particles popping in and out of existence. These fluctuations are governed by Heisenberg's uncertainty principle, which permits temporary violations of energy conservation on very small scales and for very brief periods. Some physicists have speculated that in the post-heat death universe, after unimaginable eons have passed, a sufficiently large quantum fluctuation might occur by sheer chance, creating a region of space with lower entropy. If this fluctuation were large enough, it might serve as the seed for a new Big Bang, restarting the cycle of cosmic evolution in a localized region. The probability of such a fluctuation is almost inconceivably small, requiring timescales that make the current age of the universe seem instantaneous by comparison. Yet given infinite time, even the most improbable events eventually occur. The question becomes whether such fluctuations would create a new universe similar to our own, or something quite different. Related to quantum fluctuations is the concept of Boltzmann brains, named after the 19th century physicist Ludwig Boltzmann, who first considered such possibilities. A Boltzmann brain is a fully formed conscious entity that arises from random fluctuations rather than evolutionary processes. In the post-heat death universe, given enough time, quantum fluctuations might produce not just new Big Bangs, but also isolated pockets of complexity, including potentially conscious observers. This leads to a troubling philosophical question known as the Boltzmann brain paradox. If random fluctuations can create both conscious observers and entire universes, and the former require far smaller fluctuations than the latter, then most conscious observations would be made by Boltzmann brains rather than observers like us who evolved in a full universe with a consistent history. The fact that we observe a consistent, ordered universe suggests either that something is wrong with our understanding of cosmic evolution and entropy, or that mechanisms exist to prevent the formation of Boltzmann brains. Beyond these scientifically grounded speculations, more exotic possibilities for universal reboot can be imagined. Perhaps our universe exists within a higher dimensional black hole in another universe, with our Big Bang corresponding to the formation of that black hole. When the higher dimensional black hole evaporates through Hawking radiation, it might spawn a new universe in its place. Or perhaps intelligence itself might play a role in cosmic renewal. Some futurists and philosophers have suggested that sufficiently advanced civilizations might develop the technology to create new universes, either through artificial Big Bangs in laboratory settings or through the engineering of black holes with specific properties. In this view, intelligent life becomes part of the mechanism by which the cosmos perpetuates itself. String theory and its extension, M theory, suggest yet another possibility, that our universe is just one manifestation of an underlying mathematical structure capable of generating countless different universes. The same fundamental equations that describe our universe might, with different initial conditions or parameters, describe entirely different universes with different physical laws. In this landscape of possible universes, the death of one might have little meaning for the broader mathematical reality that contains them all. Each of these scenarios faces significant challenges, both theoretical and empirical. Many rely on physics beyond the standard model, incorporating speculative ideas from quantum gravity, string theory, or other frameworks that remain unconfirmed. Others require fine-tuning or special initial conditions that seem contrived, and perhaps most importantly, most of these scenarios are currently untestable, falling outside the reach of experimental verification. Yet they remain valuable as explorations of the limits of our understanding, as attempts to extend the story of the cosmos beyond what seems like a bleak conclusion. They remind us that physics is an evolving discipline, that our current theories, however successful, may be incomplete, and that the universe may hold possibilities beyond our current imagination. As we consider these various reboot scenarios, we might also reflect on what it would mean for a new universe to arise after the heat death of our own. Would it bear any relationship to our universe? Would any information, structure, or pattern from our cosmos survive into the next? Or would the new universe begin entirely fresh, with no memory or trace of what came before? Most of the mechanisms we have discussed would create new universes that are causally disconnected from our own. The patterns and structures that evolved in our universe, from galaxies to planets to living beings, would leave no imprint on the new creation. The achievements of intelligence, the beauty of art, the discoveries of science, all would vanish without trace. Each universe would write its own story, isolated from those that came before. Yet there might be subtler connections. The laws of physics that governed our universe might shape the formation of the next, creating a kind of inheritance at the deepest level. Or in scenarios like Penrose's conformal cyclic cosmology, mathematical patterns might persist across the boundary between cycles, even if no material or energy crosses that divide. In contemplating these possibilities, we confront our desire for permanence, for meaning that transcends the finite duration of any particular cosmic epoch. We want the universe and ourselves as part of it to matter in some ultimate sense. The idea that everything we know might dissolve into a featureless equilibrium, leaving no trace and no sequel, challenges our intuitive sense of narrative and purpose. But perhaps meaning does not require permanence. Perhaps significance lies not in eternal duration, but in the patterns, relationships, and experiences that emerge during the universe's active phase. The fact that stars shine for billions rather than trillions of years does not diminish their beauty. The fact that life exists for a cosmic eye blink rather than forever does not reduce its value. Each moment in the cosmos has its own intrinsic worth, regardless of what follows. Moreover, our understanding of the far future remains profoundly limited. The heat death scenario follows from our current best theories, but those theories continue to evolve. The discovery of dark energy, now central to our cosmic model, was unknown just decades ago. What other fundamental aspects of reality might we still be missing? Aspects that could completely change our vision of the cosmic future. In this sense, scientific humility demands that we hold our predictions lightly. Yes, the evidence currently points toward an eventual heat death, but the path of science has never been a straight line, and our understanding of the cosmos continues to deepen and occasionally to radically shift. The final chapters of the cosmic story may contain surprises beyond our current theories or imagination. For now, we can marvel at the fact that we exist in a universe complex enough, ordered enough, and comprehensible enough that we can even pose these questions. We inhabit a privileged moment in cosmic history when matter has organized into structures capable of contemplating their own origins and ultimate fate. In our brief window of existence, we glimpse the vast sweep of cosmic evolution, from the Big Bang to the potential heat death and beyond. Whether our universe ends in eternal stillness or somehow seeds the birth of new cosmos, the journey itself has a majesty that transcends its ultimate destination. We are the universe aware of itself, matter contemplating matter, the cosmos reflecting on its own extraordinary story. Endings may also be beginnings if only we could see further. As we venture into the furthest reaches of the cosmic timeline, beyond the heat death and any potential universal reboot, we approach a domain where our understanding of physics becomes increasingly tenuous. These are realms where time itself takes on new meaning, where the foundations of our scientific understanding begin to crack, and where the questions we ask may be fundamentally different from those that have guided us thus far. Welcome to the frontiers of knowledge, where physics as we know it begins to break down. Time, that seemingly fundamental dimension of our reality, undergoes profound transformations in the post-heat death universe. In our daily experience, time flows steadily and uniformly, marking the progression from past to future. We perceive time's arrow through processes that have a clear direction, like the cooling of a hot cup of tea, the aging of our bodies, or the dispersion of a drop of ink in water. These directional processes are manifestations of the second law of thermodynamics, the tendency for entropy to increase. But in a universe that has reached maximum entropy, where energy is distributed as evenly as possible and no significant temperature gradients exist, these directional processes cease. Without the increase of entropy to define a preferred direction, time loses its arrow. Past and future become almost indistinguishable, not because time stops flowing, but because nothing happens that could define its direction. This situation forces us to reconsider what time actually is. Is time merely our perception of change, a mental construct we use to order sequential events? Or does it exist independently, a fundamental dimension of reality that continues even when change becomes imperceptible? Philosophers have debated these questions for centuries, but the heat-death universe brings them into sharper focus. In relativity theory, time is inseparably woven together with space to form a four-dimensional continuum called spacetime. The geometry of space-time is shaped by the distribution of matter and energy, creating the curvature we experience as gravity. In the early universe, with its concentrated energy and rapid expansion, this geometry was dynamic and ever-changing. But in the post-heat death universe, with energy dispersed evenly and expansion continuing at a constant rate, space-time approaches a simpler, more static geometry. What does it mean for consciousness to exist in such a universe? Our perception of time seems intimately linked to the sequence of thoughts and experiences that constitute our awareness. We measure time subjectively by the changes in our mental states. But in a universe where change becomes vanishingly rare, could consciousness as we understand it even exist? And if it did, how would it experience the near-eternal sameness of the heat-death state? These questions lead us to the concept of Boltzmann brains, those hypothetical conscious entities that might form from random quantum fluctuations in an otherwise equilibrium universe. If such entities could exist, their experience of time would be radically different from our own. Rather than perceiving a continuous flow of events in a causally connected world, a Boltzmann brain might experience only a brief moment of consciousness, containing perhaps false memories of a past that never existed, before dissolving back into the void. The possibility of Boltzmann brains highlights a profound challenge to our understanding of reality in the far future universe. In a cosmos at equilibrium, given enough time, quantum fluctuations will produce all possible configurations of particles up to a certain size, with smaller configurations occurring more frequently than larger ones. A human-sized brain, with its specific arrangement of neurons and synapses, represents one such possible configuration. While astronomically unlikely at any given moment, over the effectively infinite time available after heat death, such fluctuations become not just possible, but inevitable. This leads to the disturbing thought that in the post-heat death universe, most instances of consciousness might be isolated Boltzmann brains, rather than evolved organisms in structured environments. These random assemblages of particles that happen to form brain-like configurations would vastly outnumber conventional observers like ourselves, raising questions about what constitutes a typical conscious experience in the universe across its entire history. Philosophers call this the Boltzmann brain paradox, the troubling implication that random fluctuations should produce many more isolated brains with illusory memories than actual evolved observers in structured universes. The fact that we find ourselves in the latter category suggests either that something is wrong with our understanding of cosmic evolution and quantum fluctuations, or that the universe is much younger than it appears, or that additional physical principles constrain the formation of Boltzmann brains. Beyond these philosophical puzzles, the post-heat death universe challenges our understanding of quantum mechanics itself. In quantum theory, physical systems are described by wave functions that evolve over time, according to the Schrödinger equation. This evolution is deterministic and reversible, meaning that in principle, one could run the equation backward to determine the past state of a system from its present state. But the heat death represents a state of maximum entropy, a destination toward which all physical systems tend, but from which they do not spontaneously depart. This apparent conflict between the reversibility of fundamental physics and the irreversibility of thermodynamic processes constitutes what physicists call the arrow of time problem. In the post-heat death universe, with its effective cessation of thermodynamic processes, would quantum mechanical evolution continue in a meaningful sense? Some theories suggest that, in such a state, quantum wave functions might decohere so rarely that the universe effectively freezes, not just thermodynamically, but quantum mechanically as well. Others propose that quantum fluctuations would continue indefinitely, occasionally producing significant deviations from equilibrium that might, in the most extreme cases, seed new cosmic structures or even new universes. The vacuum itself, that seemingly empty space that constitutes most of the universe, becomes a focal point for these questions. In quantum field theory, the vacuum is not truly empty, but instead contains fields that fluctuate continuously due to the uncertainty principle. These fluctuations give rise to virtual particles that pop in and out of existence, borrowing energy from the vacuum for their brief manifestation. In the current universe, these vacuum fluctuations occur against a background of real particles, electromagnetic radiation, and gravitational fields. But in the post-heat death universe, with matter decayed and radiation redshifted to near nothingness, the vacuum fluctuations would constitute almost the entirety of physical activity. The universe would become a quantum vacuum, seething with virtual particles, but almost entirely devoid of stable structures. This raises profound questions about the nature of existence itself. If the universe consists primarily of fleeting quantum fluctuations with no enduring patterns or structures, in what sense does it meaningfully exist? Does reality require persistence, or can it consist of momentary states with no causal connections between them? And how would the concept of physical law apply to such a universe, where statistical descriptions might become the only meaningful ones? The breakdown of physics as we know it extends to our most fundamental theories. General relativity, our best description of gravity and space-time, treats space as a continuous fabric that can bend and stretch in response to matter and energy. But quantum mechanics suggests that at the smallest scales, space itself might be discrete, composed of minimal units that cannot be further subdivided, much like pixels on a computer screen. In the post-heat death universe, as energy disperses to nearly homogeneous distribution, the scale at which quantum effects of gravity would become important recedes to ever smaller distances. The conflict between the continuous space-time of general relativity and the potentially discrete nature of quantum space becomes increasingly relevant. But without the energy concentrations needed for experimental probes of these smallest scales, the nature of space-time at the quantum level remains perpetually beyond direct investigation. Similarly, our understanding of time at the quantum level remains incomplete. Some approaches to quantum gravity, like loop quantum gravity, suggest that time might be quantized as well, composed of discrete moments rather than flowing continuously. Others, like certain interpretations of string theory, treat time as emergent rather than fundamental, arising from more basic entities that themselves exist timelessly. In the far future universe, with its near absence of change or causal processes, these different conceptions of time might become indistinguishable in practice. Whether time flows continuously or proceeds in discrete ticks, whether it is fundamental or emergent, might make no observable difference in a universe at equilibrium. The questions themselves might cease to be scientifically meaningful and instead become purely philosophical. This transition from scientific to philosophical questions marks another way in which physics breaks down in the far future. Science as we practice it relies on observation, measurement, and the testing of hypotheses against empirical data. But in a universe without structure, without significant events, and without observers that evolved within a causal framework, the empirical foundation of science dissolves. What remains are mathematical structures and logical arguments divorced from experimental verification. Yet, even as conventional physics reaches its limits, new forms of understanding might emerge. In a universe dominated by quantum fluctuations, statistical descriptions might take precedence over deterministic ones. The relevant questions might shift from what will happen next to what patterns are most likely to emerge from the quantum foam and with what frequencies. The distinction between ontology, the study of what exists, and epistemology, the study of how we know what exists, might blur or even reverse. In a universe where observer and observed, subject and object, become indistinguishable quantum fluctuations in the void, the nature of knowledge itself transforms. The question becomes not just what can we know about the universe, but what does it mean for the universe to know itself through the fleeting moments of awareness that arise within it. These philosophical dimensions of the far future universe remind us that physics, for all its mathematical precision and empirical success, represents just one approach to understanding reality. As physics reaches its limits, other modes of inquiry, from philosophy to mathematics, to modes of understanding we cannot yet imagine, might become increasingly relevant. Perhaps the most humbling aspect of contemplating the far future universe is the recognition of our own limitations. Our minds evolved to understand the middle scales of reality, the everyday world of objects, energies, and timeframes relevant to our survival. We extend our understanding beyond these scales through mathematics, technology, and collective intellectual effort, but we inevitably reach boundaries beyond which our concepts begin to fail. Time as we understand it, causality as we experience it, existence as we conceptualize it, all emerge from our particular perspective as complex organisms in a universe far from equilibrium. As the universe approaches equilibrium in the far future, these concepts may become increasingly inadequate. New concepts, perhaps unimaginable to us now, might be needed to describe the reality of a universe at or near the heat-death state. And yet, there is profound beauty in pushing our understanding to its limits, in glimpsing, however faintly, the furthest future of the cosmos we inhabit. Even if our concepts ultimately fail, even if our theories break down, the journey of understanding itself has value. We are the universe becoming aware of itself, matter contemplating its own nature and destiny, the cosmos reflecting on its extraordinary story from beginning to end. In this reflection, we find perhaps the deepest meaning of our existence, not in permanence, which seems denied by the physics of entropy, but in the momentary miracle of comprehension, in the brief window when the universe develops structures complex enough to contemplate their own origins and ultimate fate. We cannot know what comes next, only that time continues, even if nothing else does. While the heat death presents the most widely accepted scenario for the ultimate fate of our universe, it is not the only possibility that physicists have explored. The future of the cosmos depends critically on the properties of dark energy, the nature of the vacuum, and our understanding of fundamental physics, all areas where significant uncertainties remain. In this chapter, we will explore alternative endings to the cosmic story, fates both more sudden and more dramatic than the quiet fading of the heat death. The Big Crunch represents perhaps the most direct alternative to the gradually expanding, cooling universe we have described thus far. In this scenario, the current expansion of the universe eventually halts and reverses, leading to a cosmic contraction where all matter and energy collapse back toward a singularity similar to the Big Bang. For this to occur, the gravitational attraction between all matter in the universe would need to overcome the momentum of cosmic expansion. This would require either that the universe contains far more matter than currently observed, or that dark energy, which currently drives accelerating expansion, changes its nature over time. If the universe began to contract, the process would in many ways mirror cosmic expansion in reverse. Distant galaxies would gradually appear to move closer rather than farther away. The cosmic microwave background radiation would blue shift rather than red shift, increasing in energy rather than diminishing. The average density of matter and energy would rise steadily, but the contraction would not precisely reverse the earlier expansion. During contraction, entropy would continue to increase rather than decrease. Structures would not simply revert to earlier, more organized states. Instead, as everything compressed into an increasingly small volume, temperatures would soar, galaxies would collide and merge, stars would be ripped apart by tidal forces, atoms themselves would eventually disintegrate as the fundamental forces merged under extreme conditions. The final moments of the Big Crunch would see all matter compressed to unimaginable density and temperature, perhaps forming a singularity where the known laws of physics break down completely. Some theories suggest that this singularity might lead to a bounce and subsequent re-expansion, creating a new universe, as discussed in our previous chapter on universal reboots. However, current observations of cosmic expansion make the Big Crunch scenario appear increasingly unlikely. The discovery of dark energy and the measurement of the universe's flat geometry both suggest that cosmic expansion will continue indefinitely rather than reversing. But this could change if our understanding of dark energy proves incomplete. At the opposite extreme from the Big Crunch lies the Big Rip, a scenario where cosmic expansion accelerates so dramatically that it eventually tears apart all structures, from galaxy clusters down to atoms themselves. The Big Rip becomes possible if dark energy is not a constant cosmological constant, as currently believed, but rather a more dynamic entity called phantom energy, whose density actually increases over time. This would cause the expansion of space to accelerate without bound, eventually reaching a point where the expansion becomes so rapid that gravitationally bound systems cannot maintain their integrity. In this scenario, the destruction would proceed hierarchically, from largest to smallest structures. First, galaxy clusters would be pulled apart as the space between them expanded too rapidly for gravity to hold them together. Next, individual galaxies would disintegrate, then stellar systems, with planets being pulled away from their stars. Eventually, stars and planets themselves would be torn apart, followed by molecules, atoms, and finally even subatomic particles. The Big Rip represents cosmic doom at its most dramatic, a violent end to the universe where everything is literally torn asunder by runaway expansion. The timeline for such an event, if phantom energy exists, could be as soon as a few tens of billions of years from now, far sooner than the heat death or big crunch scenarios. Current observations constrain the properties of dark energy, but do not completely rule out the phantom energy required for a Big Rip. Continued measurements of cosmic expansion may eventually determine whether this spectacular end awaits our universe. A third alternative to the heat death, perhaps the most unsettling of all, is the possibility of vacuum decay. This scenario emerges from our understanding of the quantum vacuum, the seemingly empty space that pervades the universe. In quantum field theory, the vacuum is not truly empty, but instead represents the lowest energy state of all the quantum fields that permeate space. But there is a possibility that our vacuum is not in the absolute lowest energy state possible, but rather in what physicists call a metastable false vacuum, a local minimum in the energy landscape that could tunnel to a lower energy true vacuum. If a transition to a lower energy vacuum state began somewhere in the universe, it would spread outward at nearly the speed of light, creating a bubble of new vacuum with different physical properties. Inside this bubble, the fundamental constants of nature, the very laws of physics, would be drastically altered. The mass of elementary particles, the strength of fundamental forces, even the dimensionality of space might change. Such alterations would be catastrophic for all existing structures. Stars would cease fusion and collapse or explode. Chemical bonds would no longer be stable. Complex structures like living organisms would disintegrate instantly. Not even atoms could survive in their current form if the underlying physical constants changed significantly. The vacuum decay scenario is particularly disturbing because it could happen at any time, without warning. The bubble of true vacuum would expand at nearly light speed, giving no time for evacuation or preparation, even if such responses were possible. One moment the universe would exist as we know it, the next it would be transformed into something entirely different, inhospitable to all existing forms of matter. How likely is vacuum decay? Our current understanding suggests the false vacuum would be extremely long-lived, stable for timeframes far exceeding the current age of the universe. But certain events, like high-energy particle collisions or extreme gravitational fields near black holes, might trigger a transition. The fact that the universe has existed for billions of years without undergoing such a transition provides some reassurance, but not absolute certainty. A fourth alternative fate for the universe is sometimes called the Big Freeze or Cosmic Freeze, which shares some similarities with the heat death but differs in key aspects. In this scenario, cosmic expansion continues indefinitely, but without the thermodynamic equilibrium that characterizes the heat death. The Big Freeze focuses on the physical separation of matter rather than its thermodynamic state. As cosmic expansion accelerates due to dark energy, all structures not bound by gravity or other forces become increasingly isolated. Eventually, each galaxy or galaxy cluster becomes effectively alone in its observable universe, with all other structures having receded beyond the cosmic horizon. Within these isolated pockets, normal processes continue. Stars burn out, matter breaks down through various decay processes, and entropy increases. But unlike in the heat death scenario, complete thermodynamic equilibrium is never reached because the accelerating expansion continually enlarges the available volume, preventing the homogeneous distribution of energy that defines the heat death. The end state is a universe of isolated islands, each containing the remnants of a galaxy or galaxy cluster, surrounded by ever-expanding empty space. Within each island, conditions might eventually approach something like the heat death, but on the larger scales, the universe remains perpetually out of equilibrium due to its ongoing expansion. Beyond these major scenarios, physicists have explored even more exotic possibilities. Some theories suggest that the universe might eventually undergo a phase transition, similar to water freezing into ice, where space-time itself crystallizes into a new structure with different properties. Others propose that quantum effects might eventually dominate, creating a kind of quantum patchwork universe where different regions follow different physical laws. The conformal cyclic cosmology proposed by Roger Penrose, which we discussed in the context of universal reboots, can also be viewed as an alternative to the heat death. In this model, the universe never truly reaches a state of perfect equilibrium, but rather transitions from one eon to another, with the remote future of each eon becoming, through a conformal transformation, the Big Bang of the next. As we consider these various scenarios for cosmic doom, it is worth reflecting on the levels of certainty we can assign to each. The heat death remains the most widely accepted fate because it follows most directly from established physics, the second law of thermodynamics in particular, combined with our observations of an accelerating cosmic expansion. It requires the fewest additional assumptions or speculative physics. The Big Crunch would require either far more matter than we have detected, or a fundamental change in the nature of dark energy. Current observations make this scenario increasingly unlikely, but not impossible. The Big Rip depends on dark energy having specific properties that remain within the bounds of possibility, but appear less likely based on current measurements. More precise observations of cosmic expansion may eventually rule this scenario in or out. Vacuum decay involves quantum field theory operating in domains we cannot directly test with current technology. While the possibility cannot be dismissed, the long-term stability of our universe suggests that if our vacuum is indeed metastable, it is likely to remain so for timeframes far exceeding the current age of the universe. The Big Freeze or cosmic freeze represents a variation on the heat death that differs primarily in emphasis, rather than in fundamental physics. The distinction lies in whether thermodynamic equilibrium can truly be achieved in an ever-expanding space. What unifies all these scenarios despite their differences is that they represent extrapolations of our current understanding of physics into domains far beyond direct observation or experiment. They are scientific in the sense that they follow logically from established theories, but they involve timescales and conditions so extreme that empirical verification may remain forever beyond our reach. This highlights an important aspect of cosmology as a science. It often operates at the boundaries of what can be directly tested. We make observations of the current universe and construct models that both explain these observations and make predictions about the future. But as we project further forward in time, our confidence necessarily decreases. The uncertainty inherent in these predictions should not be seen as a weakness, but rather as an honest acknowledgement of the limits of our knowledge. Science advances not just by asserting what we know, but by carefully delineating what we do not know. And cosmic eschatology, the study of the end of the universe, pushes these boundaries to their furthest extent. Moreover, our understanding of fundamental physics remains incomplete. We have yet to reconcile quantum mechanics with general relativity in a comprehensive theory of quantum gravity. Dark energy, which plays a crucial role in determining the universe's fate, remains poorly understood. New discoveries or theoretical breakthroughs could dramatically alter our vision of the cosmic future. In the face of this uncertainty, scientific humility seems the appropriate stance. We can outline possibilities based on our best current understanding, but we should remain open to revision and refinement as our knowledge grows. The ultimate fate of the universe may well involve processes or principles that we have not yet glimpsed, possibilities beyond our current theories or imagination. This humility extends to the philosophical dimension of cosmic eschatology. The end of the universe raises profound questions about meaning, purpose, and value that transcend purely scientific considerations. What significance should we attach to processes unfolding over timescales that dwarf not just human history, but the lifetime of stars and galaxies? How does the finitude of the cosmos, whatever form that finitude takes, shape our understanding of our own briefer existence? Different cultures and philosophical traditions have grappled with these questions in various ways. Some find meaning precisely in the transiency of existence, valuing the present moment all the more because it passes. Others seek consolation in the persistence of patterns or mathematical structures, even as their physical manifestations dissolve. Still others look to values or meanings that transcend physical processes entirely. Science cannot resolve these philosophical questions, but it can inform them by clarifying what endings are physically possible and what time frames they might involve. By expanding our temporal horizon to encompass the full arc of cosmic evolution, from the Big Bang to these various potential endings, science provides a context for our reflections on meaning and purpose. As we contemplate these different dooms, we might find ourselves drawn to certain scenarios over others, perhaps preferring the gradual fade of the heat death to the violent sundering of the Big Rip, or finding more aesthetic appeal in the cyclic universe than in the one-way journey to equilibrium. These preferences reveal something about our values and sensibilities, about what kinds of stories we find compelling or consoling. But the universe unfolds according to its own principles, indifferent to our preferences or anthropocentric notions of narrative satisfaction. The cosmos that produced us, that evolved the capacity for self-reflection through beings like ourselves, follows laws that operate on scales far beyond human experience or intuition. Its story may not conform to our desire for neat beginnings, middles, and ends. Perhaps the most profound insight from studying these various cosmic dooms is not which one will ultimately occur, but rather the remarkable fact that we can contemplate them at all. We, collections of atoms arranged in patterns of extraordinary complexity, can use mathematics and observation to project the fate of the entire cosmos over timeframes that make our species' existence seem instantaneous by comparison. We are the universe aware of itself, matter reflecting on its own ultimate destiny. Doom comes in many forms, some slow, some sudden or final. Throughout our journey across cosmic time, we have focused primarily on the physical processes that will shape the universe's evolution, from the fading of stars to the evaporation of black holes. But there is another player in this cosmic drama, one whose future role remains both fascinating and profoundly uncertain. Life, that remarkable phenomenon that has emerged at least once in the universe, may yet have a significant part to play in the long future of the cosmos. When we speak of life in this context, we must broaden our perspective beyond the familiar carbon-based forms that inhabit Earth. Life, in its most general sense, might be understood as a complex, self-sustaining pattern capable of replication, adaptation, and evolution. While the only example we know with certainty is Earth's biosphere, the fundamental principles that govern life here might apply to vastly different substrates and environments elsewhere in the universe. The question we now consider is how long such patterns could persist as the universe ages, cools, and approaches its ultimate fate. Could life, in any form, survive the death of stars, the decay of matter, or the dispersal of energy into an ever-expanding void? And if it could survive, what role might it play in shaping the cosmos toward which it journeys? In our current stelliferous era, life as we know it depends directly on the energy provided by stars. Photosynthesis captures the energy of sunlight, forming the foundation of Earth's food web. This process, or analogous energy capturing mechanisms, likely represents a universal requirement for life on planets orbiting stars. But stars are temporary phenomena. As we explored earlier, even the longest-lived red dwarfs will eventually exhaust their hydrogen fuel and fade away. As stars begin to die, any intelligent civilizations that have evolved around them would face an existential challenge. Either they must find ways to survive without their parent star, or they must migrate to younger stars that still burn brightly. Both approaches present enormous technical challenges, but might not be insurmountable for a sufficiently advanced civilization. Migration between star systems requires overcoming the vast distances of interstellar space. While current human technology makes such journeys prohibitively slow and energy-intensive, future civilizations might develop propulsion systems capable of reaching significant fractions of light speed. Generation ships, where multiple generations live and die during the journey, represent one approach. Suspended animation or radical life extension might provide alternatives. Even more exotic possibilities include the digital uploading of consciousness, where minds are transferred to computational substrates that could be sent between stars at much lower energy cost than biological bodies. Or perhaps civilizations might send the instructions for recreating themselves rather than the individuals themselves, seeding new worlds with their biological or technological descendants. For civilizations that choose to remain with their dying star, different strategies become necessary. As red dwarf stars enter their final phases, they gradually increase in luminosity before beginning their long, slow cooling. Advanced civilizations might adapt to these changing conditions, perhaps moving their habitats to different orbits as the star's output fluctuates, or developing technologies to regulate the temperature of their environments regardless of stellar conditions. As stars finally exhaust their nuclear fuel and begin cooling as white dwarfs, they continue to emit significant thermal radiation for trillions of years. A civilization might construct a tightly orbiting habitat that captures this heat, using it to power essential functions. Freeman Dyson, the physicist who explored many of these long-term survival strategies, suggested that life might even evolve to function at progressively lower temperatures, adapting its metabolic processes to extract useful energy from ever-cooler environments. Beyond relying on the residual heat of stellar remnants, advanced civilizations might tap more exotic energy sources. Black holes, in particular, offer intriguing possibilities. Though we typically think of black holes as objects that trap energy rather than release it, they actually represent the universe's most efficient energy storage mechanisms. Through a process called black hole farming, a civilization might feed matter into a rotating black hole in a carefully controlled manner, extracting energy from the accretion disk of superheated material that forms around it. This technique could yield enormous amounts of energy, potentially sustaining a civilization for far longer than stars could provide. Even more efficient would be tapping the rotational energy of a black hole through a process called the Penrose process, named after physicist Roger Penrose. By dropping matter into a spinning black hole along specific trajectories, a civilization could extract some of the black hole's rotational energy. Theoretically, up to 29% of a black hole's mass energy could be extracted this way, an amount that dwarfs the roughly 1% efficiency of stellar nuclear fusion. As the universe continues to age and expand, energy gathering becomes increasingly challenging. In the degenerate era, after stars have died but before matter has completely decayed, civilizations might mine the universe for its remaining resources, gathering the cold remnants of stars and planets to construct enormous computers or habitats optimized for minimum energy consumption. These structures might be designed to power down most of their operations for long periods, waking briefly to perform essential functions before returning to dormancy. In this way, a pattern recognizable as life or intelligence might persist for vastly longer than would be possible with continuous operation. The concept of a hibernating or pulsating civilization, cycling between activity and dormancy, becomes increasingly relevant as the universe ages. By synchronizing its wake periods with the availability of energy or the occurrence of rare events worth observing, such a civilization might stretch its existence across timeframes that would otherwise be inaccessible. As we move further into the future, beyond the degenerate era and into the black hole era, even these strategies become increasingly difficult to maintain. With matter decayed and black holes representing the only significant concentrations of energy, life would face its greatest challenge yet. Any surviving intelligence would need to adapt to an increasingly cold, dark, and empty universe. One speculative possibility is that advanced civilizations might create isolated pockets of reverse entropy, regions where energy remains concentrated enough to support complex processes. These pockets would be temporary by necessity, but might provide islands of habitability in an otherwise inhospitable cosmos. By moving between such islands, or creating new ones as old ones disperse, intelligence might continue its journey even through the black hole era. Perhaps the most extreme adaptation would be for life to fundamentally alter its nature, transitioning to forms that require minimal energy and operate on timescales vastly different from our own. Consciousness might be slowed to the point where subjective millennia pass in what the external universe would measure as eons. In this way, the gradual dispersal of energy might appear, from the perspective of such beings, to happen at a manageable pace. But there is another possibility, one that transforms life from a passive survivor of cosmic evolution to an active participant in shaping the universe's future. Some physicists and futurists have speculated that sufficiently advanced civilizations might eventually develop the capability to influence cosmic parameters, alter the laws of physics in limited regions, or even create new universes. This concept of cosmological engineering represents perhaps the ultimate expression of intelligence's potential role in the long future. Rather than merely adapting to an increasingly hostile universe, life might reshape its environment on the grandest scale imaginable. One version of this idea suggests that advanced civilizations might learn to create baby universes, new cosmoses that bud off from our own through artificial quantum fluctuations or carefully engineered black holes. These new universes might inherit some characteristics from their parent universe, including perhaps the physical parameters necessary for the emergence of life. If such universe creation is possible, it raises the fascinating possibility of a form of cosmic reproduction and selection. Universes that produce intelligent life capable of creating new universes would have more descendants than those that do not. Over many generations of universe creation, physical parameters might evolve toward values that maximize the production of intelligence, creating a kind of cosmological natural selection. This scenario, while highly speculative, offers a potential answer to the puzzle of our universe's apparent fine-tuning for life. The physical constants that govern fundamental forces and particles seem exquisitely calibrated to allow for the emergence of complexity. If universes can reproduce through the actions of intelligent life, and if the physical parameters of child universes resemble those of their parents, then the multiverse might naturally evolve toward life-friendly conditions. Another form of cosmological engineering involves attempts to prevent or postpone the heat death. While current physics suggests that the increase of entropy is inevitable, some have speculated that advanced civilizations might develop techniques to counter this tendency, at least locally. Perhaps by manipulating dark energy, creating specialized black holes, or exploiting currently unknown physics, intelligence might extend the habitable period of the universe far beyond what natural processes would allow. Even if the heat death cannot be prevented entirely, intelligence might influence how the universe approaches this end state. By carefully shepherding resources, organizing matter and energy in patterns that maximize future possibilities, advanced civilizations might leave their mark on the cosmos even as it winds down toward equilibrium. The simulation hypothesis offers yet another perspective on life's potential role in the far future. This idea suggests that sufficiently advanced civilizations might create detailed simulations of universes, complete with conscious inhabitants who experience their simulated reality as we experience our own. If such simulations are possible and likely to be created in large numbers, then most conscious experiences might occur within simulations rather than in baseline reality. In the context of the dying universe, the simulation hypothesis takes on new significance. As physical reality becomes increasingly hostile to life, advanced intelligences might transfer their existence primarily to simulated realities, where the constraints of the external universe have less impact. Within these simulations, they could experience rich, complex existences, even as the physical substrate supporting these computations operates in a universe approaching heat death. Of course, such simulations would still require energy to run, and this energy would still be subject to the physical laws of the universe containing the computers. But the efficiency of computation might improve dramatically over cosmic timescales, allowing far more subjective experience to be extracted from each unit of available energy. This leads to a profound philosophical question about the nature of existence in the far future universe. If most conscious experience occurs in simulated realities rather than in direct interaction with the physical world, what constitutes the true history of the cosmos? Is it the gradual dispersal of energy in the physical substrate, or the potentially much richer and more complex events occurring within simulations? The answer may depend on what we value about existence. If we prioritize conscious experience, the capacity for thought, emotion, then the simulated worlds might represent the most significant aspect of the universe's long future. If we prioritize physical reality, independent of observers, then the simulation layer might seem less fundamental. The persistence of life and intelligence into the deep future faces one inescapable limitation: the continuing expansion of the universe. As space stretches, the average energy density decreases, to gather sufficient energy to maintain complex processes. Eventually, even the most efficient civilization would find it impossible to collect enough energy to perform meaningful computation or maintain organized. This suggests that while life might extend its existence far beyond the stelliferous era and possibly even into the black hole era, it likely cannot survive indefinitely in an eternally expanding universe. The heat death, or something functionally equivalent to it, appears to represent an ultimate horizon beyond which organized complexity cannot persist. Yet even with this limitation, the potential longevity of life and intelligence dwarfs the timeframe of biological evolution on Earth thus far. If life emerges early in a universe's history, as it has in ours, and if intelligence develops the capacity for technological adaptation, as it has at least once, then conscious experience might persist for trillions of years or more, orders of magnitude longer than the roughly 4 billion years of Earth's biosphere. This vast potential future for life provides a different perspective on our current moment in cosmic history. We exist relatively early in the habitable period of the universe, when stars still shine abundantly and matter remains organized in complex structures. The future history of life, should it continue beyond Earth, might be far longer and perhaps far stranger than its past. Our awareness of this potential future connects us to processes extending far beyond our individual lives or even our species' existence. We are, potentially, the ancestors of beings who might witness the death of the last stars, who might harvest energy from black holes, who might reshape the very fabric of reality to extend the habitable period of the cosmos. This connection does not guarantee such a future, of course. Life remains vulnerable, especially in its early technological phases when it has the power to destroy itself, but perhaps not yet the wisdom to avoid doing so. The vast potential future for intelligence could be cut short by catastrophe, whether natural or self-inflicted, but the possibility remains, a potential written into the physics of our universe and the adaptability of life as we know it. As we contemplate the role of life in the long future, we might find both humility and a kind of cosmic significance. Humility, because even the most advanced civilizations cannot escape the fundamental constraints of entropy and expansion. Significance, because through life, the universe has developed the capacity to understand itself, to make choices about its future, and perhaps to influence its evolution in ways that purely physical processes could not. In the darkening cosmos, as stars fade and galaxies disperse, the light of consciousness might continue to shine, adapting to each new challenge, finding ways to persist in an increasingly hostile environment. Whether through migration, hibernation, transformation, or cosmic engineering, life represents the universe's most remarkable response to its own inevitable dissolution. Even in decline, the universe may whisper to those who listen. We have journeyed far into the cosmic future, witnessing the fading of stars, the dissolution of galaxies, the evaporation of black holes, and the potential persistence of life against increasingly impossible odds. Now we approach perhaps the most poignant moment in our cosmic story, the time when the last detectable photon of light moves through the void, when the final particle decays, when the universe reaches a state so close to perfect equilibrium that no further meaningful events occur. This is the last light, the final flicker in the cosmic story. To understand this endpoint, we must consider the fundamental constituents of our universe and their ultimate fate. Matter, as we experience it, is composed of particles organized in various structures, from atoms to molecules to stars and living beings. The complex arrangements that form our familiar world depend on the stability of these particles, particularly protons, which form the nuclei of atoms. But as we have discussed in earlier chapters, there are theoretical reasons to suspect that protons might not be truly stable. Grand unified theories, which attempt to unify the electromagnetic, weak and strong nuclear forces, generally predict that protons will decay with a half-life of perhaps 10 to the power of 36 years. While this timescale is so vast that no proton decay has yet been detected in laboratory experiments, over the almost unlimited time available in the far future, even processes of such extreme rarity become inevitable. If protons do decay, they would transform into lighter particles, typically a positron and a neutral pion, which quickly decays into photons. Each decay releases a tiny amount of energy, a final contribution to the universe's light budget from matter that might have once formed stars, planets, or even living beings. Imagine the universe at a time perhaps 10 to the power of 40 years from now. The stars have long since burned out. The stellar remnants have cooled to near absolute zero. The black holes have evaporated through Hawking radiation. What remains is an extraordinarily dilute soup of elementary particles, primarily electrons, positrons, neutrinos, and photons, separated by distances that make the current gap between galaxies seem microscopic by comparison. In this cold, dark expanse, proton decay would represent one of the only ongoing processes. Each decay would produce a brief flash of gamma radiation, a momentary punctuation in the cosmic silence. Initially, these decays would occur relatively frequently across the universe, given the vast number of protons that once existed. But as time passes and more protons decay, these events would become increasingly rare. Eventually, perhaps 10 to the power of 100 years from now, the vast majority of protons would have decayed. The matter that once formed the cosmic structure would exist primarily as radiation and leptons, those elementary particles like electrons and neutrinos that appear to be truly stable. The universe would consist almost entirely of these particles, along with the dark energy that continues to drive cosmic expansion. In this environment, the concept of the last light takes on a literal meaning. There would come a time when the final proton in what we now consider the observable universe undergoes decay. This single event, the transformation of the last remnant of baryonic matter into radiation, would mark a significant milestone in cosmic evolution. The universe would move from having at least some structure based on matter to being composed almost entirely of free radiation and leptons. The photons released in this final decay would travel through the virtually empty cosmos, their wavelengths gradually stretching due to the continuing expansion of space. Over incomprehensible spans of time, these photons would redshift until their wavelengths became larger than the observable universe itself, effectively fading from any possibility of detection. If protons are actually stable, contrary to current theoretical expectations, other processes would still eventually transform all complex matter. Quantum tunneling would allow particles to overcome binding forces given enough time, causing all bound structures to disintegrate. Gravitational radiation would cause any orbiting systems to lose energy and collapse. Even in the absence of proton decay, the universe would still progress toward a state where all matter exists in its simplest possible forms. But the concept of the last light extends beyond just the final decay of matter. It encompasses the last event that meaningfully changes the state of the universe, the final moment when anything happens that could be considered significant by any potential observer. In the far distant future, long after proton decay has transformed most matter into radiation, quantum fluctuations would continue to occur. These random variations in quantum fields, permitted by Heisenberg's uncertainty principle, represent perhaps the only true source of novelty in an otherwise static cosmos. Most of these fluctuations would be microscopic and insignificant, but given enough time, larger fluctuations might occasionally occur. Quantum mechanics allows for particles to spontaneously appear from the vacuum, borrowing energy for their brief existence before disappearing again. In the post-proton decay universe, such quantum fluctuations would create occasional particles and antiparticles that quickly annihilate, producing brief flashes of energy. These tiny events would be the universe's heartbeat, rare and irregular, but theoretically continuing indefinitely. Could such fluctuations ever produce something more significant? Quantum theory suggests that given enough time, any configuration of particles that does not violate conservation laws might spontaneously form through random fluctuations. The probability decreases exponentially with the complexity of the configuration, making macroscopic fluctuations astronomically unlikely. But in the context of an eternal or near-eternal future, even the most improbable events eventually occur. This leads to a profound question about the meaning of the last light. Is there truly a final event, a last significant occurrence, after which the universe remains forever unchanged? Or does the possibility of quantum fluctuations mean that the cosmos never truly reaches a state of perfect stasis, that novelty remains possible, if vanishingly rare, throughout an infinite future? The answer depends partly on whether the universe continues expanding indefinitely. If dark energy maintains its current properties, cosmic expansion will indeed continue forever, constantly diluting the energy density of the universe. This ongoing expansion creates an interesting tension with quantum fluctuations. As space stretches, the probability of significant fluctuations decreases, as particles would need to form closer together to interact. But the expansion never reaches a point where fluctuations become strictly impossible, just increasingly improbable. In such a universe, we might think of the last light not as a single, final event, but as the transition to a state where events become so rare that the universe approaches, but never quite reaches, perfect equilibrium. The light never fully goes out. It just becomes so infrequent that darkness dominates almost completely. From a more philosophical perspective, we might ask whether events that occur with no observer to witness them truly happen in a meaningful sense. If a quantum fluctuation produces a photon in a universe where no structures exist that could possibly detect it, does this count as a significant event? If a complex pattern briefly forms from random fluctuations but dissolves before any intelligence could evolve to comprehend it, has something meaningful occurred? These questions touch on deep issues in the philosophy of physics and consciousness. They ask us to consider what constitutes reality beyond observation and what gives events significance in a cosmos that may be devoid of meaning, making entities for the vast majority of its existence. As we contemplate the last light, we might also consider what it means for time itself. In our current universe, with its complex structures and irreversible processes, time has a clear direction determined by the increase of entropy. But in a state very close to maximum entropy, with only rare and isolated events occurring, the arrow of time becomes blurred. Without significant changes to mark the passage of time, without processes that clearly distinguish the past from the future, time takes on a different character. Physicists debate whether time would continue to flow in a meaningful sense in such a universe, or whether it would become essentially static from a macroscopic perspective, with only quantum fluctuations providing any sense of change or duration. Perhaps time itself, at least as we understand it, fades along with the last light. There is something profoundly moving about the image of the last light, the final photon dancing through an otherwise dark and empty cosmos. It represents the endpoint of a journey that began with the extraordinary energy and complexity of the Big Bang. From an initial state of perfect order but extreme disequilibrium, the universe evolved through a period of incredible creativity, forming atoms, stars, planets, and perhaps life, before gradually winding down toward its quiet conclusion. This narrative arc from order through complexity to dissolution reflects a fundamental truth about our universe: its inexorable movement from low entropy to high entropy states. The last light marks the final step in this great cosmic journey, the point where organized energy has been converted almost entirely to disorganized energy, where structure has given way to near-perfect homogeneity. Yet there is beauty even in this ending. The last photon, traveling through the void, carries with it the echo of everything that came before. It is the final testament to a universe that once blazed with the light of countless stars, that harbored the complexity of life, that achieved, however briefly, the miracle of self-awareness through beings capable of contemplating their own origins and ultimate fate. In a sense, the significance of the last light lies not in the event itself, which might be no different from countless similar events that preceded it, but in what it represents: the completion of a cosmic story that spans from the first moments of creation to the final fading of all structure and organization. For any intelligence that might somehow witness or conceptualize this event, the last light would carry tremendous emotional and philosophical weight. It would represent both an ending and a kind of perfection, the universe having completed its journey from the extraordinary disequilibrium of the Big Bang to the perfect equilibrium of the heat death. Perhaps most remarkably, through the existence of conscious beings like ourselves, the universe has developed the capacity to anticipate this ending, to project forward through unimaginable spans of time and envision its own ultimate fate. We are the universe aware of itself, matter contemplating its own distant future dissolution. This awareness creates a kind of bridge across time, connecting our brief moment of existence to the far future we will never witness. Through science and imagination, we reach across the eons, grasping, however tentatively, the the final fate of the cosmos that gave us birth. In doing so, we participate in a remarkable form of time travel, not of the body, but of the mind, extending our understanding far beyond the narrow slice of time we physically inhabit. The last light also invites us to reconsider our place in the cosmic story. We exist in the universe's bright youth, when stars still burn and complex structures can form and persist. Our moment in cosmic history is special precisely because it is temporary, a brief window when the conditions for life and consciousness exist. Before us stretch the simplicity of the early universe. After us stretches the simplicity of the heat death. We inhabit the complex middle, the time of structure and organization, of life and mind. This perspective might offer both humility and a kind of cosmic significance. Humility, because we see ourselves as just one chapter in an immensely longer story, a momentary flourish in a narrative that began long before us and continues long after. Significance, because we represent one of the ways the universe has found to know itself, to reflect on its own nature and destiny. As we imagine that final photon, the last light moving through an otherwise dark and empty cosmos, we might see it as carrying not just energy, but meaning. It is the universe's final communication with itself, the last echo of a creation that once roared with energy and complexity. In its solitary journey through the void, it embodies both the impermanence of all structures and the completion of a perfect cosmic cycle. When the last photon dances into the abyss, the story ends. When the last proton has decayed, when the final photon has stretched beyond detection, when the universe has reached a state so close to perfect equilibrium that no meaningful events occur, what remains of all that came before? Is there any sense in which the rich history of our cosmos persists? Any lingering echo of the stars and galaxies, the planets and perhaps civilizations that once existed? This question brings us to the concept of cosmic memory, the ways in which the universe might retain traces of its past, even in its final state. One form of cosmic memory lies in the distribution of particles throughout the universe. Even after reaching thermal equilibrium, the specific arrangement of fundamental particles, their exact positions relative to one another, would in principle contain information about the universe's history. Like a shuffled deck of cards that retains the memory of how it was shuffled in the precise order of its cards, the universe's final state encodes its evolutionary path. However, this information becomes increasingly inaccessible as time passes, with particles separated by ever-growing distances due to cosmic expansion, and with quantum uncertainty blurring their exact positions and momenta. Reconstructing the universe's history from its final state would become practically impossible. The information exists in theory, but cannot be read or utilized. Another, more robust form of cosmic memory might exist in the form of gravitational waves. These ripples in space-time, generated by the movement of massive objects, travel through the universe at the speed of light. Unlike electromagnetic radiation, which interacts readily with matter, gravitational waves pass through most material almost undisturbed, carrying information about their sources across vast distances and timeframes. The most significant gravitational waves in cosmic history were generated by violent events, the mergers of black holes and neutron stars, the explosions of supernovae, and perhaps the quantum fluctuations of the inflationary epoch immediately after the Big Bang. These waves continue to propagate through space long after their sources have disappeared, carrying echoes of events that occurred billions or even trillions of years in the past. As the universe expands, these gravitational waves stretch, their wavelengths increasing and their amplitudes decreasing. But unlike light, which can be absorbed or scattered by matter, gravitational waves travel virtually unimpeded, preserving their information content even as they weaken. In the far future universe, these faint ripples in space-time might represent the most enduring record of the dynamic processes that once shaped the cosmos. However, even gravitational waves face an ultimate limitation. As cosmic expansion continues, driven by dark energy, the wavelengths of ancient gravitational waves would eventually stretch beyond the scale of the observable universe. At this point, they would cease to be detectable even in principle, their information lost to any potential observer within our cosmic horizon. a more subtle form of cosmic memory exists in the very structure of spacetime itself. According to Einstein's general relativity, mass and energy curve spacetime, creating the effect we experience as gravity. While massive objects like stars and black holes create the most dramatic curvature, every particle contributes to the overall geometry of the universe. This curvature, once established, does not immediately disappear when the matter that created it moves or transforms. Like ripples spreading from a stone thrown into a pond, the effects of matter on spacetime can persist after the matter itself has changed form. In the post-proton decay universe, with matter converted primarily to radiation, the curvature of spacetime would still carry faint imprints of the structures that once existed. The memory encoded in spacetime curvature faces the same ultimate fate as gravitational waves. As cosmic expansion continues, these subtle geometric patterns would stretch and flatten, eventually becoming undetectable against the background of quantum fluctuations in the fabric of spacetime itself. The information would dilute beyond recovery, though never completely vanishing in a mathematical sense. Perhaps the most profound form of cosmic memory lies in the correlations between particles that once interacted. Quantum mechanics tells us that when particles interact, they become entangled, their properties correlated in ways that persist even when they move far apart. This quantum entanglement creates a kind of memory that connects particles across vast distances and potentially across immense spans of time. In the early universe, when matter was densely packed and interactions frequent, particles became entangled in complex networks. As the universe expanded and these particles separated, they carried with them the quantum signatures of these early interactions. Even after proton decay has transformed most matter into radiation, these correlation patterns would persist in the relationships between the resulting particles. Quantum information theory suggests that information is never truly lost in fundamental physical processes, only scrambled or made practically inaccessible. The entanglement patterns created throughout cosmic history would, in this view, still exist in the far future universe, though so diluted by expansion and complicated by subsequent interactions that reconstructing the original information would be effectively impossible. These various forms of cosmic memory, from the distribution of particles to gravitational waves to spacetime curvature to quantum correlations, suggest that the universe never completely forgets its history. The information about what once existed becomes increasingly inaccessible, but remains encoded in subtle patterns that persist even in the final state of near-perfect equilibrium. There is something both comforting and unsettling about this persistence. Comforting because it suggests that nothing that occurs in the universe is ever truly lost, that the stars and galaxies, and perhaps civilizations that once existed, leave an indelible, if faint, mark on the cosmos. Unsettling, because this persistence seems ultimately meaningless if no intelligence remains to detect these patterns or reconstruct the information they contain. This brings us to a profound question about the nature of information and meaning in the universe. Does information have significance if it cannot be accessed or utilized? If the history of the cosmos remains encoded in its final state, but no consciousness exists to reconstruct this history, does this encoding matter in any meaningful sense? Different philosophical traditions would approach this question in different ways. Some might argue that information has intrinsic value independent of observers, that the mathematical patterns themselves represent a kind of reality, regardless of whether they are perceived. Others might contend that information only becomes meaningful through the act of interpretation, that patterns acquire significance only when intelligence recognizes and utilizes them. This question connects to broader debates about realism and idealism in philosophy, about whether reality exists independently of perception or is in some sense constituted by the act of observation. It asks us to consider whether the universe's memory has meaning in itself or only through its potential relationship to consciousness. A related question concerns the possibility that some form of intelligence might persist into the far future universe, adapting to the increasingly challenging conditions as discussed in our previous chapter. If consciousness could survive in some form, perhaps by becoming ever more efficient in its use of energy or by entering extended periods of dormancy, it might maintain the capacity to access at least some of the information encoded in the universe's final state. Such an intelligence might serve as the universe's memory keeper, preserving knowledge of the cosmos's history, even as the physical traces of that history fade toward imperceptibility. Through technology, or through adaptations we can scarcely imagine, it might maintain a connection to the past that would otherwise be lost. This scenario, while highly speculative, offers an alternative to the complete dissolution of meaning in the far future. It suggests that the echoes of what was might not only persist physically in subtle patterns, but could remain alive in the awareness of beings who carry forward the torch of consciousness into the darkening cosmos. Even without persistent intelligence, we might consider another form of cosmic memory, one that transcends the physical universe entirely. The mathematical structures that describe our cosmos, the equations of general relativity and quantum mechanics, the patterns and symmetries that underlie physical processes, exist in a sense independently of their physical manifestations. These mathematical realities, accessible to any intelligence that evolves the capacity for abstract thought, represent a kind of Platonic memory of the universe, the eternal forms that shape the transient physical world. In this view, even if all physical traces of cosmic history eventually fade beyond detection, the mathematical truths that govern this history remain eternally valid and potentially discoverable. This perspective suggests a kind of immortality for the patterns that define our universe, if not for the specific physical instantiations of these patterns. The particular stars and galaxies may disperse, but the laws that govern their formation and evolution persist as mathematical truths, accessible in principle to any intelligence that develops the conceptual tools to grasp them. As we contemplate these various forms of cosmic memory, we might also consider a more metaphorical sense in which the universe remembers its history. The second law of thermodynamics, with its insistence that entropy always increases in closed systems, gives time its arrow and ensures that the future differs from the past. In this sense, the high entropy final state of the universe implicitly contains its low entropy beginning, as the endpoint of a thermodynamic process always contains information about its starting conditions. The heat death represents not just any high entropy state, but the specific high entropy state that evolved from the particular low entropy conditions of the Big Bang. Like the final position of water at the bottom of a hill contains information about the path it took to get there, the universe's final state reflects the specific journey it undertook from order to disorder. This thermodynamic memory, while abstract, connects the end of the universe to its beginning in a deep and fundamental way. The cosmic story comes full circle, from the extraordinary order of the Big Bang, through the complex structures that developed as this order dissipated, to the quiet conclusion where order has been fully converted to disorder. The end state remembers the beginning through the very fact of the entropic process that led from one to the other. For us, existing in the complex middle period of cosmic history, these considerations about the universe's memory have a peculiar poignancy. We are, in a sense, the universe's most advanced memory system currently known, the only entities within the cosmos that actively preserve and interpret information about its history and structure. Through science, art, culture, and individual consciousness, we maintain a representation of reality that would otherwise be lost to entropy. Our capacity to remember, to record, to understand patterns represents one of the ways the universe has developed to preserve information against the tide of increasing entropy. We push back against the second law, creating local pockets of order and meaning, even as the cosmos as a whole moves toward greater disorder. We are the universe remembering itself, matter organized in such a way that it can contemplate its own past and future. This perspective offers a kind of cosmic significance to consciousness, and particularly to the scientific enterprise. By discovering the laws that govern reality, by reconstructing the history of the universe from the evidence available to us, we participate in the cosmos's self-documentation. We create a memory that, while physically transient, represents the universe's own awareness of its nature and evolution. Perhaps most remarkably, through our scientific understanding, we can project forward to the far future scenarios we have been exploring, anticipating the fading of structure and the near erasure of information that awaits in the distant cosmic future. We reach across time to grasp the eventual fate of all things, creating a kind of mental time travel that connects our brief moment of existence to the ultimate destiny of the universe that produced us. In this way, we serve as a bridge between past and future, a moment when the cosmos achieves sufficient complexity to contemplate both its origins and its end. We are the universe aware of itself, matter reflecting on matter, a brief but brilliant flash of self-knowledge in the long arc of cosmic evolution. As we imagine the far future universe, with its subtle patterns preserving faint echoes of what once was, we might take comfort in the knowledge that nothing is ever truly lost, that information in some form persists even as the structures that created it dissolve. The stars that shone, the worlds that formed, the lives that flourished, all leave their mark on the fabric of reality, a mark that fades but never completely vanishes. Whether or not this persistence has meaning in the absence of intelligence to interpret it remains an open question, one that touches on our deepest assumptions about the nature of reality and value. But the fact that we can even pose such questions, that we can contemplate the echoes of existence that remain after everything else has faded, speaks to the remarkable capacity for reflection that has emerged, however briefly, in our corner of the cosmos. Even when nothing remains, the echo of existence lingers. Our journey through cosmic time has taken us from the vibrant universe we know today to the furthest reaches of the future, where time itself becomes a different concept. We have witnessed the fading of stars, the dissolution of galaxies, the evaporation of black holes, and the quiet dispersal of energy into an ever-expanding void. We have contemplated the end of everything, not with fear, but with wonder and curiosity. As our exploration draws to a close, let us pause to reflect on what it means to exist in a universe with both a beginning and an end, a cosmos with its own life cycle, its own story that spans from the explosive creativity of the Big Bang to the serene quietude of the heat death. There is a profound beauty in impermanence. The stars above us shine, not in spite of their finite lives, but because of them. Their brilliance comes from the very processes that will eventually extinguish them. The complex atoms that form our bodies exist because previous generations of stars lived and died, scattering their elemental creations across space. We are made of star stuff, as Carl Sagan famously observed, the descendants of cosmic processes that stretch back to the beginning of time. Think of the oxygen in your lungs, forged in the heart of a star that exploded perhaps billions of years ago. Consider the iron in your blood, created only in the final catastrophic moments of a massive star's life. The calcium in your bones, the carbon in your cells, all these elements were once scattered across interstellar space before gravity gathered them into our solar system, into our planet, and eventually into the living structure you now inhabit. This connection to the larger cosmic story gives our brief lives a context that transcends our individual existence. We are not separate from the universe, but an integral part of it, a momentary arrangement of matter and energy that has, remarkably, developed the capacity for self-awareness. We are the universe experiencing itself, consciousness emerging from complexity, mind arising from matter. Our ability to comprehend cosmic timescales represents a kind of miracle, evolved to deal with the immediate challenges of survival. Our minds can nevertheless stretch to encompass billions of years past and trillions of years future. Through science and imagination, we reach far beyond our physical limitations, grasping at least conceptually the vast sweep of cosmic evolution from beginning to end. Imagine holding in your mind the first moments after the Big Bang, when the universe was a searingly hot plasma of elementary particles. Follow the cooling and expansion as atoms formed, then stars, then galaxies. See the emergence of our solar system from a swirling disk of dust and gas, the gradual evolution of life on Earth over billions of years, and then look forward, past the death of our sun, past the fading of all stars, into the unimaginably distant future we have explored together. This comprehension offers both humility and significance. Humility, because we see ourselves as just one fleeting chapter in an immensely longer story, a momentary flourish in a narrative that began long before humanity and continues long after. Significance, because our consciousness allows the universe to know itself, to reflect on its own nature and destiny, to find meaning in patterns that would otherwise unfold unwitnessed. The fate of the universe we have explored, its gradual winding down toward equilibrium, may seem at first glance a melancholy conclusion. We naturally resist the thought of endings, of dissolution, of the fading of all the complex structures that give our reality its character and beauty. But there is a kind of peace in this ultimate cosmic fate, a completion of the great arc from order through complexity to quietude. In some Eastern philosophical traditions, this cycle mirrors the path of spiritual development, from the initial differentiation of self from other, through the rich complexity of lived experience, to the eventual dissolution of boundaries in a state of enlightenment or union with the fundamental nature of reality. What physics describes as the heat death, these traditions might see as the universe returning to its natural state of equilibrium, the completion of a great cosmic exhalation. Even from a purely scientific perspective, there is something elegant about the universe's journey toward maximum entropy. The same laws that enabled the formation of stars and galaxies, planets, and perhaps living beings also ensure the eventual dissolution of these structures. The story has integrity precisely because it follows from consistent principles throughout its unfolding. As you drift now towards sleep, imagine yourself floating among the stars, untethered from the brief moment we call the present. Feel the cosmic timescales stretching out around you, the billions of years past, the trillions of years yet to come. See the galaxies spinning, their spiral arms glittering with the light of billions of stars. Watch as new stars form from clouds of gas and dust, their nascent light pushing back against the gravitational collapse that created them. Observe the dance of binary stars, circling each other in gravitational embrace. Witness the death of massive stars in supernova explosions, momentarily outshining entire galaxies before fading into luminous nebulae. See the birth of planetary systems, rings of debris gradually coalescing into worlds of rock and gas and perhaps occasionally life. And then see them slowly fading, dissolving, returning their energy to the void from which they emerged. Watch as the last stars exhaust their fuel, as the stellar remnants cool to darkness, as the great cosmic structures disperse into the expanding vacuum. Feel the gentle settling of the universe into its final state, not as an ending to be feared, but as the natural completion of a magnificent process. There is no fear in this cosmic cycle, only wonder at the extraordinary dance of energy and matter, space and time. We are privileged to exist during the universe's bright youth, when stars still burn and complex structures can form and persist. Our moment in cosmic history is precious, precisely because it is temporary, a brief window when the conditions for life and consciousness exist. Consider the remarkable chain of events that led to your existence. The particular arrangement of atoms in your body has never existed before and will never exist again in exactly the same way. The specific configuration of neurons that creates your consciousness, your memories, your sense of self, represents a unique expression of cosmic possibility. You are, quite literally, unrepeatable, a one-time collection of particles that has taken this precise form only now, only here. Yet, you are also connected to everything else in the cosmos through unbroken chains of causality, stretching back to the Big Bang. The atoms in your left hand and the atoms in your right hand were once, in the early universe, close enough to interact directly. Now they find themselves reunited in your body, after journeys lasting billions of years, through stars and interstellar clouds, through planetary formation and chemical evolution. Perhaps the most remarkable aspect of our existence is that we can contemplate the entire sweep of this cosmic story, from beginning to end. Through science and mathematics, observation and theory, we reconstruct the past and project the future, creating a mental model of reality that spans from the first moments after the Big Bang to the final fading of structure into near-perfect equilibrium. In doing so, we transcend the limitations of our physical existence. Though our bodies are confined to a tiny slice of cosmic space and time, our minds reach across the universe and deep into both past and future. We achieve a kind of immortality, not of the body, but of understanding, connecting our brief moment of awareness to the full arc of cosmic evolution. This connection offers a perspective on our lives that both diminishes and enhances their significance. Diminishes because we see how tiny our existence is against the vast backdrop of cosmic time. Enhances because we recognize the extraordinary improbability of our existence, the precise calibration of physical constants and cosmic conditions required for us to be here at all. As you continue to drift towards sleep, let this dual awareness of transience and wonder fill your consciousness. Feel yourself as both infinitesimally small and infinitely significant, a brief arrangement of stardust that has, against astronomical odds, developed the capacity for self-reflection, for appreciation of beauty, for contemplation of the cosmos that gave you birth. The universe asks nothing of us but to exist, to experience, to perhaps understand a small portion of its workings. It offers no intrinsic purpose beyond what we create, no meaning beyond what we discover. But in that freedom lies a profound opportunity, the chance to find our own significance within the grand cosmic context, to create meaning that acknowledges both our transience and our connection to the entire sweep of existence. As sleep approaches, imagine once more the far future universe we have explored together. See the last stars fading, their light growing dimmer as they exhaust their nuclear fuel. Watch the white dwarfs cooling over trillions of years, their once blinding surfaces fading to dull red, then infrared, then darkness. Observe the black holes, those most patient of cosmic objects, gradually returning their hoarded energy to the universe through Hawking radiation, their event horizons shrinking over unimaginable spans of time. See the final protons decaying, converting the last vestiges of matter into radiation. Watch as this radiation stretches and cools in the ever-expanding space, its wavelengths growing longer, its energy dispersing ever more thinly. Feel the universe approaching its ultimate state of equilibrium, a cosmos of perfect homogeneity, where energy is distributed as evenly as possible throughout an immense and still expanding void. But see also the subtle patterns that persist, the faint echoes of what once was, the mathematical truths that transcend physical dissolution, the information about everything that ever existed, encoded in correlations so subtle they can never be detected, yet in some abstract sense eternal. The universe remembers, even when no consciousness remains to access these memories. Perhaps most importantly, see the completion, the fulfillment of cosmic potential, the universe having expressed all possible forms and structures permitted by its physical laws before returning to quietude. There is perfection in this cycle, a beginning, middle, and end that together form a complete and coherent story. Our own lives mirror this cosmic pattern, emerging from the undifferentiated potential of early development, expressing our unique complexity through growth and experience, and eventually returning our elements to the larger cycles of nature. We are fractal expressions of the universe itself, recapitulating in our brief existence the same patterns that play out across billions of years of cosmic evolution. Consider the rhythms of your life, the cycles of waking and sleeping, activity and rest, engagement and withdrawal. Each day has its own arc from the quiet of dawn through the complexity of full wakefulness to the settling of consciousness as sleep approaches. Each breath follows a similar pattern, the inhalation that builds energy, the momentary pause at full expansion, the exhalation that releases and relaxes, the brief stillness before the cycle begins again. In this resonance between the macrocosm of universal history and the microcosm of individual life, we find perhaps the deepest connection to the cosmos that created us. We are not merely in the universe, we are of it, expressions of the same principles that govern its grandest scales, participants in the same journey from order through complexity to dissolution. And so, as consciousness fades into sleep, as thoughts dissolve and awareness dims, embrace this small daily echo of the cosmic cycle. Trust in the process that brings you back to awareness with each new day, just as the universe itself might someday cycle back to a new beginning through processes we can only dimly envision. Feel your breathing slow, your thoughts grow quiet, your body heavy and relaxed. The same gravity that holds the stars in their courses anchors you now to Earth, binding you to the planet that has been home to all human generations. The same atomic forces that power the stars work within each cell of your body, maintaining the intricate dance of molecules that constitutes your living form. As you hover on the edge of sleep, imagine once more the cosmos in all its vastness. From the subatomic scales where quantum uncertainty reigns, to the largest structures of galactic superclusters stretching across billions of light years. See yourself as a nexus of consciousness within this immensity, neither insignificant nor supreme, but perfectly positioned to witness and wonder at the universe's unfolding. Sleep now under the stars that were. Dream with galaxies that drift beyond time, and remember, even in the end, there is peace. The universe was, and that is enough.